Nebulae are warmly colored when photographed. They appear as a luminous region, rich in ionized gas ejected from stars or unused during their formation. The gas and dust present in the interstellar medium can materialize when excited by stellar radiation or backlit. This is how nebulae are classified. Emitting nebulae are gaseous formations that produce their own luminescence. They absorb light from a nearby hot star and emit it at lower energies in a variety of colors. They are said to be bright, as opposed to reflective nebulae, which simply reflect the light of nearby stars. Also known as IC 2177, the Seagull Nebula is a huge emission nebula. Seen from Earth, it is as large as 4 times the diameter of the full moon. The reddish glow of atomic hydrogen dominates, dotted with luminous young stars that stretch the length of the nebula. The name Seagull Nebula comes from its strong resemblance to the silhouette of a bird. This cosmic cloud is an ideal place for the formation of new stars. The Seagull Nebula is located 3,800 light-years from Earth and has a diameter of around 100 light-years. It contains several open clusters, including NGC 2343, NGC 2335, Calinder 465, and Calinder 466. This nebula is difficult to observe even under ideal viewing conditions, as its apparent magnitude is +10. The large number of stars in the nebula makes it impossible to see. The wings are almost impossible to see, unlike the head, referenced NGC 2327, which contains fewer stars. This is a region of compact emission in which a massive star is enclosed. There are several categories of emission nebulae. HII regions. These are regions of intense activity in which stars form. The Orion constellation is home to one of the most famous examples, the Orion Nebula, or M42. Its proximity to the Earth makes it one of the best-known and most studied nebulae by scientists. Within the Orion Nebula, numerous stars and even planetary disks form. The nebula glows with fluorescence. Excited by the ultraviolet radiation of bright stars, gas atoms emit light. The color emitted depends on the type of atoms. Hydrogen, which is clearly in the majority in nebulae, emits predominantly red light, as does sulfur. Oxygen, on the other hand, emits green. Although our eyes are particularly poor at distinguishing colors at night, the Great Orion Nebula is an exception to this rule. Its contrasts allow observers to easily distinguish the nebula's colors. At first glance through binoculars, the Orion Nebula appears as a small cloud among the stars of Orion's sword. When viewed through a 60 to 80 millimeter telescope, its central region reveals a greenish hue. The jade hue intensifies when viewed through a more powerful telescope. As for the red, it remains indistinguishable, as our eyes are blind to this color at night. The accumulation of gas over tens of thousands of billions of kilometers gives the Orion Nebula a dense appearance, but this is only an illusion. The Orion Nebula has been known since ancient times. Astronomers have been observing it through telescopes for almost 4 centuries. As if petrified since the dawn of time, nothing in this immense interstellar cloud has ever moved. But it's only the nebula's enormous distance, almost 1,500 light-years, that makes us from Earth insensitive to its violent disturbances. This nebula is one of the largest in our Milky Way. It extends over a diameter of 24 light-years. Its mass is 2,000 times greater than that of our Sun. And yet, for all its immensity, it remains almost empty. Barely a few hundred atoms are present per cubic centimeter. The Orion Nebula is illuminated by 4 supergiant stars, forming an asterism that identifies the Orion trapezoid. Each of these stars shines 100,000 times brighter than the Sun. Their powerful ultraviolet radiation heats the gas, making it luminescent. As a result, the hydrogen clouds take on a flamingo pink hue, while the oxygen veils emit green radiation. These 4 supergiant stars don't just make light, they provoke a powerful stellar wind, blowing at over 100,000 kilometers per hour, or 62,000 miles per hour. Space is violently swept away, carrying clouds like storm clouds. Compressed gas becomes denser, and gravitation kicks in. Small globules of gas and dust form. They measure a few tens of billions of kilometers and resemble eggs that flatten on themselves under their own weight. As they collapse, the gas and dust that make them up are set into rotation. At the heart of these stars, a star is born. Having attracted matter to itself, it slowly pulls it out, blowing it around and beginning to shine. The 4 stars of Orion's trapezoid were born in this way around 200,000 years ago. By blowing the gas that gave them birth around them, they seed space and trigger the birth of new stars. The phenomenon of emission makes it possible to study nebulae using selective filters that exclude certain lines from the spectrum. Planetary nebulae are brightly colored and highly structured. They are associated with the death of low-mass stars like the Sun. Planetary nebulae are produced by the slow expulsion of gas from the surface layers of a star's atmosphere at the end of its life. All stars of mass equal to or less than the Sun end their lives by scattering the upper layers of their atmosphere into the surrounding medium. The material takes on a relatively regular disk shape, reminiscent of a planet. In fact, at the time of William Herschel's first observations, he observed the small star that remained visible at the center of the nebula, surrounded by a pale disk that gave the false impression that a planet was being born. Stars of greater mass also produce injections when they die, but these are much more brutal. The result is a supernova, or SNR for short. Although planetary nebulae and SNRs can sometimes be confused, there are many differences between them. Many planetary nebulae are easily accessible to professional and amateur astronomers from Earth. These include the Lyra Nebula M57, the Dumbbell Nebula M27, the Rosette Nebula NGC 2237-9, the Owl Nebula M97, and the Helix Nebula NGC 7293. The discovery of this type of nebula is well within the reach of amateur astronomers. 139 candidate planetary nebulae have been proposed, and some 20 have been confirmed. The Lyra Nebula is the most representative of all planetary nebulae. This star appears as a magnificent corona, surrounding the star as it dies out. The star's core is completely exposed, still glowing and illuminating the gas around it. The white dwarf at the center of the Lyra Nebula reaches 100,000 degrees Celsius, or 180,000 degrees Fahrenheit. By comparison, the Sun reaches 5,500 degrees Celsius. It has much more extensive extensions than the main ring, certainly the result of material ejected by the star before the nebula itself was formed. Planetary nebulae provide information not only on the star's constitution, but also on the date on which it expelled matter, by calculating the expansion velocity of the gases. The impressive dynamism of planetary nebulae is reflected in some cases by gas moving at speeds of up to 5,000 kilometers per second, or 3,100 miles per second. This creates exceptional shock waves and turbulent zones. Once the star has ejected up to 35% of its envelope, it ends its life as a dwarf star. One of the closest planetary nebulae to Earth is the dumbbell M27 Nebula. It lies at a distance of around 650 light-years and exploded around 12,700 years ago. The Dumbbell Nebula was the first planetary nebula to be discovered. It is characterized by an original shape with two luminous lobes, giving it the appearance of a bell clapper, dumbbell, or apple core. This structure is known as bipolar and is found in other planetary nebulae, but never so pronounced. This characteristically asymmetrical shape is thought to have developed shortly before the star's death, as the dying star blew its atmosphere in two different directions. M27 is one of the largest planetary nebulae in the sky. Thanks to its age, it has expanded considerably. Although invisible to the naked eye, the Dumbbell Nebula is easily identifiable through binoculars. You can make out its dumbbell shape. Most planetary nebulae contain only a single star, but a few contain a binary system. Typically, this system consists of a very hot blue O-class star and a cooler A-class companion. The pair is rarely visible, as they are tightly packed together. The blue star emits mainly in the UV spectrum, while its companion emits in the visible spectrum, making it impossible to observe the star at the source of the excitation. Examples of double-core planetary nebulae include NGC 3132, NGC 1514, and the Boomerang Nebula. The latter is currently the coldest place in the universe. Located 5,000 light-years from Earth in the constellation Centauri, its temperature is -272 degrees Celsius, or -169 degrees Fahrenheit. It's colder than the cosmic microwave background, and the only known natural object of its kind. But why has it reached such a cold temperature? At the heart of this nebula lies a star 4 times more massive than the Sun. But this star hides a secret. 3,500 years ago, it was the result of the fusion of two other stars. Without this fusion, the gas in the nebula would not reach such extreme temperatures today. In fact, the Boomerang Nebula's low temperature is due to its gas being expelled in very large quantities and at extremely high velocities. A team of astronomers has taken into account the envelope's expansion velocity, which is 150 kilometers per second, or 90 miles per second, 10 times greater than that usually expelled by a red giant. Scientists have shown that the only way to produce such a quantity of gas at such a speed would be to use energy from the interaction of two stars. A few thousand years ago, the red giant would have trapped a companion star in its envelope. The interaction of the two stars produced an impetuous ejection of matter. The nebula is now shaped like an hourglass, 20,000 astronomical units long. This peculiar shape is due to the jet produced by the central star, which pushes back cold gas locally. Another planetary nebula containing a binary system that commands admiration for its marvelous shape is the PN M2-9 Nebula, nicknamed the Butterfly Nebula or Twin Jet Nebula. This nebula is characterized by a surprising complexity that takes the form of two wings around a heart. The core is made up of two old stars that change appearance and state to become white dwarfs. Their total disappearance will only occur in a few billion years' time. In the meantime, they never cease to amaze with their sumptuous designs. Located some 4,000 light-years from Earth in the constellation Ophiuchus, the Butterfly Nebula owes its wings to two stars of equivalent mass that emit two great expanses of gas. The smaller of the two has a mass between 0.6 and 1 times the mass of the Sun, and is already a white dwarf. Its companion is estimated to have between 1 and 1.4 times the mass of the Sun. It has already released its outer layers. The expansion of the gas that forms these fascinating butterfly wings is thought to have begun around 1,200 years ago. The nebula contains, inside a shell of gas, two jets expelling matter at a speed of over 1 million kilometers per hour, or more than 620,000 miles per hour. Scientists also recently discovered that a disk of gas 15 times larger than Pluto's orbit surrounds the two stars. It turns out that the star, which has already taken on the form of a white dwarf, is in the process of stripping its fading companion. NGC 1514, also known as the Crystal Ball Nebula, is a planetary nebula located in the constellation Taurus, some 800 light-years from Earth. It was discovered by astronomer William Herschel in 1790. The nebula is characterized by its ring-pair shape. This double structure is explained by the presence of a binary system of aging stars at the nebula's center. In concrete terms, the nebula appears as a double shell, with a very bright envelope in the center and a thinner one on the outside. At the center of the nebula, the two stars revolve around a common center of gravity, with a period of 4 to 9 days. NGC 6302, the Insect Nebula, or M2-9, also known as the Butterfly Nebula, or Caldwell 69, is a bipolar planetary nebula with one of the most complex structures ever observed in a planetary nebula. It lies around 3,500 light-years from Earth in the constellation Scorpius. As they age, stars can take on structures sometimes similar to flowers or insects. This is the case of the Insect Nebula, which has a wingspan of 3 light-years. Its central star, at the end of its life, has a temperature of over 200,000 degrees Celsius, or 360,000 degrees Fahrenheit, suggesting that it was originally very large. The white dwarf's mass is around 0.64 times that of the Sun. It is surrounded by a dense disk of gas and dust. It is the same disk that gives the nebula its hourglass-like bipolar structure. The Insect Nebula consists of 2 primary lobes. A wide dark band runs through the middle of the nebula, plunging the central star into darkness at every length. This band has an exceptional chemical composition. Scientists have detected ice crystals, quartz, and numerous silicates. The characteristic feature of the nebula is that it is composed of both oxygen-rich and carbon-rich minerals. In most cases, these minerals do not coexist. Stars are basically rich in one or the other, and the transition from the first state to the second occurs as the star ages. This suggests that the hydrocarbon molecules in the Insect Nebula were formed in an oxygen-rich environment. The Insect Nebula is prone to strange projections of matter in the part representing its wings. These jets are projected at more than 1,000 kilometers per second and asymmetrically. They intersect and form disordered structures. Some researchers have speculated that these ejections could be due to the central white dwarf merging with another star. However, in the absence of visibility at the center of the nebula, this hypothesis remains unconfirmed. A supernova defines the set of phenomena resulting from the gigantic explosion of a star at the end of its life. For a time, the supernova can shine brighter than an entire galaxy of billions of stars. From Earth, a supernova looks like a new star, when in fact it's the sign of a star's demise. A core collapse supernova is characterized by a massive star that stops producing energy from nuclear fusion in its core. It then collapses under its own gravity. A thermonuclear supernova occurs when a white dwarf has stored enough material for a companion star to reach a critical mass, triggering a thermonuclear explosion. The exploding star is totally destroyed, while the companion star may in some cases survive. When a supernova explodes, an enormous quantity of ejecta is expelled, of the order of several solar masses, at speeds of up to 10,000 kilometers per second, or 18,000 miles per second. The shock front resulting from the rapid expansion of this material forms the visible part of the afterglow. Supernova remnants are defined by the structure produced by the expanding supernova ejecta. Many slags retain a regular shape for a long time, depending on whether they have an internal energy source, such as a central pulsar, or not. To better understand supernova afterglows, let's look up to the sky. Against the stellar backdrop of the Milky Way, a pretty gray blob appears through a small 60mm telescope. With a 100 to 200mm telescope, we can see a well-defined S-shape. With an even more powerful instrument, it's possible to make out gaseous filaments floating in the sky. This is one of the best-known and most studied examples of supernova afterglow. Messier 1, or the Crab Nebula, some 6,300 light-years from Earth. This nebula reminds us that a supernova exploded at this very spot in the year 1054 in the constellation Taurus. In July 1054, Chinese astronomers spotted a new star in the Taurus constellation. They called it a guest star. However, its brilliance intensified to the point where it surpassed that of Venus. It remained visible for 3 weeks in daylight, with a magnitude of between -3 and -5, and appeared for 2 years at night. Around 7 centuries later, in 1758, the astronomer and famous comet hunter Charles Messier, while searching the sky for Halley's Comet, spotted a small nebula in the constellation Taurus. He gave it the number 1. It wasn't until 1928 that Edwin Hubble made the connection between the famous guest star of 1054 and this Messier 1 nebula, nicknamed the Crab Nebula, in reference to the expanding gas released by the supernova. It continues to grow at a speed of 1,500 kilometers per second, or 930 miles per second. The debris forming the nebula is made up of ionized helium and hydrogen, and has a temperature in excess of 10,000 degrees Celsius or 18,000 degrees Fahrenheit. It will dilute in the cosmos over the coming millennia. The Crab Nebula has a pulsar at its center, called the Crab pulsar. It rotates about 30 times per second. This pulsar emits 200,000 times more energy than the Sun, making it the most energetic pulsar known. Its diameter is estimated at 30 kilometers or 18 miles. It is responsible for the central illumination of the nebula. The nebula lies in the immediate vicinity of the ecliptic plane, making it an interesting source of radiation for studying other celestial bodies. By observing its radio waves or X-rays, it is possible to measure and study other nearby objects. Wolf-Rayet bubbles are located around Wolf-Rayet stars. These are defined as hot stars with masses tens of times that of the Sun. They are characterized by the fact that during a relatively brief phase following the main sequence, they eject the matter around their core in the form of very violent stellar winds. The core is then exposed and explodes into a supernova. Wolf-Rayet bubbles are particularly active, emitting huge quantities of gas as a result of thermonuclear reactions in their cores. The two most famous of these are the Crescent Nebula, NGC 6888, and Thor's Helmet Nebula, NGC 2359. The Crescent Nebula, NGC 6888, is located in the constellation Cygnus, some 5,000 light-years from Earth. This region is particularly renowned for its wealth of nebulae. The Wolf-Rayet star, WR136, at its center, generates violent stellar winds that push the ejected matter outwards. This cosmic bubble, some 25 light-years across, paints a splendid picture of the nebula through telescopes. The structures of the Crescent Nebula are the result of the interaction between the strong wind and matter ejected in the past. This star is nearing the end of its life and is expected to explode into a supernova. Thor's Helmet Nebula, NGC 2359, is a nebula in the Big Dog constellation, around 15,000 light-years from the solar system. It has the peculiar shape of a bubble, blown by a massive star with complex filaments. The Wolf-Rayet WR7 star at its center is extremely hot. The nebula's emerald green color is the result of strong emissions from the oxygen atoms in the cloud. Reflection nebulae are dust clouds that reflect the light of one or more nearby stars. These stars are bright enough to make the dust visible, but not hot enough to ionize the gas. Reflection nebulae are hot spots for star formation. The best known and most studied reflection nebula is that surrounding the Pleiades cluster, also known as M45. The Pleiades cluster is a celestial figure known since at least Neolithic times. Its appearance in the morning sky heralded harvest time. Although only a small number of stars are visible to the naked eye, this cluster is extremely rich, containing several thousand in all. The Pleiades cluster is around 100 million years old, and astronomers estimate that it will disperse into the Milky Way within 200 to 300 million years due to its low compactness. The blue nebula that surrounds this cluster is the beauty of the photographs. Emission and reflection nebulae form the group of diffuse nebulae, distinguished by their luminous emission. On the other hand, there are dark nebulae. The latter are regions in which dust from the interstellar medium concentrates in immense clouds that appear in starless regions. They are visible when they obscure part of an emitting or reflecting nebula. Ever since human beings decided to take an interest in the sky, they have been able to observe dark spots in regions of high stellar density that appear to be devoid of stars. They have put forward two hypotheses. Either these dark zones correspond to the distribution of stars, or they represent dark masses appearing as opaque screens. The first view was quickly discarded after the study of the celestial distribution of objects, since it is unlikely that immense starless pipes exist over lengths of several thousand parsecs. So it's not surprising that there are superpositions of dark clouds. Many known nebulous objects show absorption marks in the form of small black globules or thin opaque filaments. The density of these dark nebulae prevents the passage of light. The Milky Way has been studied from top to bottom since the invention of the telescope. This has revealed some 200 regions in the sky that appear to be devoid of stars. In reality, they contain dark nebulae with stars unable to illuminate them. The material is thus condensed and opaque to radiation, positioning itself in front of brightly lit regions of the Milky Way. To study these dark nebulae, you need to get as far away as possible from pollution and artificial light. Within them, a tiny fraction of the incident light crosses the matter barrier formed by the clouds. This makes them veritable radiation traps. Astronomers have therefore used derivative techniques such as infrared or radio to observe them. These dark clouds are neither too thick nor too dense. Infrared techniques are able to penetrate them, and observe the objects behind them. Dark nebulae are among the coldest and largest bodies in our galaxy. They are made up of molecular hydrogen and a variety of dusts whose grains, a mixture of silicate, graphite, ice, and various ferrous metals, provide sufficient opacity. Nebulae can also be distinguished by their thickness. The largest of them can contain up to 100 solar masses of dust. One of the best examples of this type of nebula is the charcoal bag. This large dark nebula occupies an area on the celestial vault equivalent to some 30 full moons. It can be found 600 light-years away in the Southern Cross constellation in front of luminous sections of the Milky Way. Spanish explorer Vicente Yanez Pinzon first spotted this dark spot in 1499. He was the navigator and commander of La Niña, one of the 3 ships that first landed in America under the command of Christopher Columbus. The nebula was nicknamed Magellan's Dark Cloud because of its opacity and in comparison with the 2 bright Magellanic clouds. Seen with the naked eye from the southern hemisphere, the charcoal bag can be spotted lurking against the stars of the Southern Cross. With binoculars, it's easy to spot thanks to its irregular contours. This coal-black nebula is so vast that it doesn't fit entirely within the field of a telescope. Nevertheless, a telescope can observe one of the most beautiful star clusters nearby. It's called the Jewel Box because its stars are compared to sparkling gems. The obscure Horsehead Nebula, also known as Barnard 33, is located in one of the youngest regions of the sky, the constellation Orion. At the end of December, during the winter solstice, the night-darkened hemisphere of Earth comes face to face with a stellar region of our galaxy. Stars, each more beautiful and brilliant than the last, light up the Milky Way like rubies, diamonds, and sapphires. The brightest and closest is Sirius. 100 times further on is the supergiant Rigel, which, along with Betelgeuse, Bellatrix, and Scythe, forms the constellation Orion. Not far from the center of this constellation, patience and perseverance are required to find the Horsehead Nebula just below the star Alnitak. Here, immense clouds of gas give birth to new stars. This nebula is made up of interstellar gas and dust that light is unable to penetrate. It is therefore invisible to the naked eye. Its horsehead shape is caused by the presence of a dense cloud of gas and dust. At the base of the head are young stars in the process of forming. The Horsehead Nebula is about 7 light-years long and lies almost 1,500 light-years from us. It does not radiate and is very dense and cold. Some nebulae are said to be chaotic because they are unique in that they are both emitting and dark at the same time. The gases they contain take on highly varied appearances, and the environment is disturbed. Examples include the Sorcerer's Nebula, NGC 7380, the IC 1318 Nebula, and the North American Nebula, NGC 7000. Close to Deneb, the brightest star in the Cygnus, lies the North American Nebula, NGC 7000, in the Cygnus constellation. It is closely accompanied by a neighboring nebula nicknamed the Pelican, IC 5070. The mass of gas contained in these 2 nebulae is estimated at 5,000 solar masses. Between them, they form the visible part of an immense hydrogen cloud. Scientists thought that the nearby supergiant star Deneb would provide them with the energy they needed to fluoresce. As it turns out, this star isn't hot enough at 8,230 degrees Celsius or 14,900 degrees Fahrenheit, and the nebula needs to be heated by a star with a temperature above 30,000 degrees Celsius or 54,000 degrees Fahrenheit. What's more, Deneb is too far from the nebula complex. The ionizing star is actually at the rear of the nebula. Its surface temperature exceeds 40,000 degrees Celsius or 72,000 degrees Fahrenheit, and it belongs to a binary system. The light emitted cuts the contours of the clouds in such a way as to remind us from Earth of the North American continent. The Swan Wall is a region reminiscent of Mexico and Central America. It is in this region of the nebula that we find the highest rate of star formation. The North American nebula is only visible in excellent skies. Although it emits a not inconsiderable light of magnitude 5, it extends over such a vast area that it is difficult to see. It covers an area more than 10 times that of the full moon. The Sorcerer's Nebula, NGC 7380, is so named because seen in profile, its contours evoke the figure of a sorcerer. From above, you can make out his hat, eye, nose, mouth, and long beard. This nebula is located in the Cepheus constellation, some 8,000 light-years from Earth. It is surrounded by an open cluster. The nebula and cluster form a favorable environment for the birth of new stars and the creation of new planets. The Sorcerer's Nebula is not easily identifiable on the celestial vault. It requires very good observation conditions, as well as the use of precise instruments such as a telescope with a diameter of at least 200 millimeters. The IC 1318 Nebula, also known as the Butterfly Nebula, is located in the constellation Cygnus. This brightly emitting nebula has a dark nebula at its center. Its circumflex shape is clearly visible in the photographs. Since 1976, another category of nebulae has also been described: integrated flow nebulae, or IFNs. An integrated flux nebula is illuminated solely by the luminous halo emitted by the entire galaxy it inhabits, the so-called integrated flux. This type of nebula has been observed in the Milky Way. These clouds are made up of dust present in the interstellar medium at all galactic latitudes. Their colors stand out in very long exposure photographs, but do not show up in binoculars or telescopes unless the optics are very bright and the observation site is shielded from artificial light. The best-known nebulae owe their success to their proximity to the Earth. Astronomers, whether professional or amateur, choose objects that are easily accessible and within reach of their instruments. Within the Milky Way, most of the nebulae observed are located close to the Sun, within a radius of 5,000 light-years between the Orion Arm and the Carina Sagittaria Arm. Nebulae in the direction of the galactic bulge are difficult to spot, as the stars and dust clouds there are far too dense. As for the rest of the universe beyond the Milky Way, it also contains some astonishing nebulae. Outside the Milky Way, it's difficult to identify specific individual nebulae with the same notoriety as those in our own galaxy. Nevertheless, there are some complex nebulous regions in other galaxies that are well known to astronomers and astronomy enthusiasts. We won't necessarily find individual planetary nebulae like those in the Milky Way. The galaxy itself may contain various nebulous regions due to star formation processes. Specific observations and discoveries may vary over time due to advances in astronomy and imaging. The brightness of the Magellanic Clouds is comparable to that of the Milky Way. In the southern hemisphere, and in the absence of light pollution, they both appear distinctly without the need for observational instruments. If you use binoculars, their characteristic shapes are clearly visible. The Large Cloud Galaxy measures the equivalent of 20 full moons lined up end to end. The Small Cloud Galaxy, on the other hand, is 3 times smaller. The Magellanic Clouds are the Milky Way's 2 largest satellite galaxies. The Large Cloud is 160,000 light-years from the Sun, while the Small Cloud is 200,000 light-years away. Although not the closest to the Milky Way, the galaxies of the Magellanic Clouds are still the easiest to observe. They are certainly ancient barred spiral galaxies, distorted by the gravitational pull of the Milky Way. The Small Cloud Galaxy contains around 3 billion stars, while the Large Cloud Galaxy has 10 times that number. Within the latter, we find one of the largest nebulae known in the universe, the Tarantula Nebula. A vast patch of interstellar fog is visible within the Large Magellanic Cloud. This is the Tarantula Nebula, also known as NGC 2070. Seeing the images of this nebula, it's easy to understand why this sprawling mixture of gas and stars is likened to a spider. Located 160,000 light-years from Earth, the Tarantula Nebula seems rather modest. But it's its remoteness that's misleading. If the Tarantula were as close to us as the Orion Nebula, it would cover a quarter of our sky and be visible even in broad daylight. Within this gigantic gaseous labyrinth lie some of the most massive stars known to man. Like a colossal matrix of stars, the Tarantula Nebula exceeds 1,800 light-years in diameter. It is the largest nebula known to date. Its star formation rate is higher than in any other region of the Milky Way. Shielded from light pollution, the nebula appears as a small bright spot in the immediate vicinity of the Large Magellanic Cloud. Its magnitude of around 5 makes it easily visible to the naked eye. At the heart of the nebula is a dense cluster of hot stars that produce the ultraviolet radiation that ionizes the surrounding gas. This is what makes the nebula visible. The cluster of stars is called R136a. It includes the most massive star ever observed. R136a1 beats the Sun in every respect. It is comparatively 30 times wider, 8 million times brighter, and has a surface temperature 10 times higher than the Sun. The nebula contains a large number of star-forming stars. It turns out that star formation in this nebula is quite different from that in other galaxies such as the Milky Way. Scientists have discovered that the star-forming regions within the Tarantula Nebula are producing stars at a far greater rate than in the Milky Way. These discoveries provide new insights into the history of stellar creation. The chemical composition of the tarantula is similar to certain star-forming regions that existed when the universe was very young, only a few billion years ago. This subject of study continues to interest scientists as they seek to learn even more about this nebula. The Tarantula Nebula emits a reddish light due to the excitation of hydrogen. The powerful light rays from giant stars burn the gas so intensely that they eventually explode into supernovas. In 1987, at the edge of the Tarantula Nebula, a supernova visible to the naked eye lit up the sky, leaving behind an afterglow that is now well known and still observed. In 1987, the Large Magellanic Cloud Galaxy was the site of the brightest supernova recorded in the last 400 years. A star with a mass equivalent to 20 solar masses exploded. SN 1987A was the first supernova explosion of the 20th century to be observed with the naked eye, far from light pollution. It was then observed continuously in all usable ranges of electromagnetic radiation. This supernova is one of astronomy's most important objects, as it is the first time that the progenitor star is known before the explosion. The phenomenon occurred on the night of February 23, 1987, some 165,000 light-years from Earth. It was the closest supernova observed outside our galaxy. Around 3 months later, in May, its brightness peaked at an apparent magnitude of around +3, before declining over the following months. The progenitor star is a blue supergiant with an initial mass of around 20 solar masses. It is named Sandelik -69°202a and formed 10 million years ago. Scientists were astonished that it was a blue supergiant and not a red one, since at the time it was considered that only red supergiants evolved into supernovas. Thanks to the Hubble telescope, scientists were able to analyze Sandelik -69°202a and deduced that it must have evolved from a red to a blue supergiant before exploding. In fact, 3 rings of gas orbit SN 1987A, dating back 20,000 years before the explosion. The star must have lost mass before its explosion, which explains its change in type. Its rings have adopted a distinctive morphology. The 2 outer rings are hourglass-shaped, while a smaller inner ring forms the neck. This characteristic may be linked to the violent solar winds that sculpted this extraordinary shape. The 2 outer rings may also have been illuminated by the gas ejected in the supernova. The supernova afterglow has always been visible. It is the object of intense observation, since it is the youngest known afterglow. All these years of observation of SN 1987A are of immense value. The data enable scientists to better understand the final stages in the evolution of stars. Supernovas are of considerable importance in the history of the universe. They expel the elements that form at the heart of stars, such as iron, oxygen, nitrogen, and carbon. Depending on the strength of the explosion, they can also feed energy into gas clouds, helping to give birth to new stars. By studying supernova 1987A from the moment of its explosion, astronomers have gained a better understanding of the very first stages in the dispersal of the afterglow, and the effects this will have on the supernova's environment. The Lobster Nebula is located in the smallest of the dwarf galaxies in the Magellanic Cloud. It spans about 400 light-years and is about 5,500 light-years from Earth. A blue glow from the emission of ionized hydrogen gas surrounds this star-forming region. The surrounding nebula appears as a mixture of gas, dark dust, stars in formation, and newborn stars. This complex architecture is the result of interactions between interstellar winds, magnetic fields, gravitational interactions, and radiation pressure. The Lobster Nebula harbors an open cluster near its center, containing stars of exceptional brilliance and mass. This is the Pismis 24 open cluster. This cluster contains many massive stars. Among them, Pismis 24-1 is 776,000 times brighter than the Sun. Its mass approaches 300 solar masses. It is, in fact, a system of at least 3 stars. Pismis 24 is one of the most active sites of massive star formation. NGC 346 is an emission nebula associated with an open cluster. It lies within the Small Magellanic Cloud in the constellation of the Toucan. It was discovered by astronomer James Dunlop in 1826. NGC 346 lies some 200,000 light-years away. This intense star-forming region has a diameter of around 200 light-years. NGC 346 is a true wonder of the southern sky. By studying it, astronomers have been able to discover a population of embryonic stars in formation. These are arranged along the dark bands of visible dust. The very young stars continue to collapse into their initial clouds, emitting a light that is reddened by the dust between them and the Earth. This stellar nursery closely resembles those that remain in the primordial universe. Scientists estimate that 2% of the 200 billion galaxies in the universe interact with a nearby galaxy. Such is the case with the famous Hound Dog Galaxy, also known as the Whirlpool Galaxy and referenced M51. It lies at an abysmal distance of 23 million light-years from us. Messier 51 is the common name for the 2 stars because Charles Messier did not split them at the time. In fact, they are a pair of interacting galaxies. The small galaxy NGC 5195 lies a few tens of thousands of light-years behind its big sister, NGC 5194. The former is so distorted by the interaction, which has been going on for almost a billion years, that astronomers can't classify it. The interaction of these 2 galaxies is causing outbreaks of new stars. In the larger of the 2 galaxies, no fewer than 100 ionized nebulae have been detected. No one knows how the encounter will end. Will the 2 stars separate and drift apart, or merge into a single galaxy? Our planet's nocturnal orientation, away from the galactic disk that illuminates summer and winter nights, is directed in spring towards the constellations with the fewest stars and interstellar gas, such as Leo, Virgo, the Big Dipper, and the Hounds. It's in these endless transparent regions of the sky, seemingly devoid of stars, that astronomers enjoy observing the most distant objects under the best conditions. Among them, the Hound Dog Spiral is one of the brightest and most beautiful galaxies known. Despite its impressive diameter of over 60,000 light-years, it is invisible to the naked eye. It is populated by over 200 billion stars. The pair of galaxies is bound together by the force of gravity. The spiral structure of NGC 5194 is strongly disrupted by the passage of its smaller companion. The galaxy's sumptuous brilliance is due to the gravitational tidal forces generated by the small galaxy. In the same way that the Moon influences the oceanic masses of the Earth, NGC 5195 acts on the gas masses of NGC 5194. This interaction suppresses interstellar gas, which condenses into new stars. As a result, the spiral disk of the Hound Dog galaxy is rich in nebulae. In close-up photographs of the galaxy's disk, we can see its youth and vitality in the brilliant nebulae illuminated by the thousands of supergiant stars they give birth to a few 100 million years ago. Only stars 1,000 to 10,000 times brighter than the Sun are visible. The billions of others are too dim to be seen individually. The barred spiral galaxy NGC 1313 is located in the constellation Reticule. It is one of the smallest and least luminous constellations in the southern hemisphere, and contains one of the most remarkable celestial objects. This galaxy lies some 13.5 million light-years from Earth. This gravitationally isolated galaxy shares some characteristics with the Magellanic Clouds. Its spiral arms are weakly coiled and attached to the end of its bar. They are uneven, revealing globules of gas. What's more, they don't rotate at the center of the bar, which is also a sign that the galaxy has undergone disturbances. Its morphology suggests that its past must have been highly turbulent. NGC 1313 is thought to have interacted with a smaller galaxy in the past. This highly active galaxy features a large number of nebulae surrounded by gas. The arms of the galaxy feature numerous star-forming sites and open clusters of young stars. The radiation from all these fledgling stars generates gas that creates beautiful patterns of light and dark nebulae. NGC 1313 is a star-forming galaxy, a feature that remains enigmatic as the galaxy remains relatively isolated. Indeed, in most galaxies of this type, the high rate of star formation is due to a meeting or even a merger of two galaxies. In the constellation Perseus, NGC 1275 is a lenticular galaxy, around 250 million light-years from Earth, with a diameter of over 250,000 light-years. This vast galaxy is characterized by highly complex dynamics that set it apart from other galaxies. Located at the heart of the Perseus galaxy cluster, it is bathed in hot, diffuse gas with an average temperature of several tens of millions of degrees. It is this gas that forms most of the luminous mass of galaxy clusters. The matter that forms the environment is highly complex. On the one hand, the hot gas causes cooling, and on the other, the supermassive black hole, with a mass equivalent to around 340 million solar masses, generates powerful, high-energy jets that prevent the gas from cooling completely. The result is a sumptuous network of filaments surrounding NGC 1275. This large nebula extends over 250 light-years, equivalent to 2.5 times the size of the Milky Way. The motion of the network of filaments is not uniform, but rather chaotic. This dynamic may be intimately linked to the heating and cooling of the gas that feeds the black hole at the heart of the galaxy. NGC 2403, also known as Caldwell 7, is a spiral galaxy in the constellation Giraffe, around 8.5 million light-years from the Milky Way. In the galaxy's eastern outer arm lies NGC 2404, an open cluster of stars. It is associated with an Emission nebula. NGC 2403's spiral arms are illuminated by bright red nebulae, a few bluish open clusters, and dark veins of dust. At its heart, the nucleus is bright but relatively small. According to some scientists, this galaxy is gravitationally part of the Messier 81 group. Around 15 million light-years from Earth, Messier 83, a spiral galaxy, is majestically visible. Beside it is a small quasi-elliptical nebula, the dwarf galaxy NGC 5253. Although it may seem rather insignificant at first glance, it is a site of intense star formation. This compact blue dwarf galaxy is located in the constellation Centauri. It has a magnitude of 10.5. It is one of the closest blue compact dwarf galaxies to us. Vivid blue and violet colors are visible through observational instruments due to its active star formation. NGC 5253 is home to very active star-forming regions, although it contains little dust, hydrogen, and helium, the basic elements for star formation. These molecular clouds strongly resemble the clouds that form the first stars in the early universe. This is why scientists like to study compact blue dwarf galaxies, to better understand the primordial process of star formation. NGC 5253 features a central starburst zone rich in hot young stars concentrated in a star cluster. Its morphology is not uniform due to the intense consumption of gas. At its heart is a gigantic supercluster of over 1 million stars, each 3 million years old. The total luminosity of this supercluster is equivalent to around 1 billion times that of the Sun. From Earth, it is completely invisible, as it is obscured by a giant dust cloud. The local group is a collection of 60 galaxies spanning 10 million light-years. Among them, the Milky Way and the Andromeda Galaxy are the main members. The third largest galaxy is the Triangulum, also known as M33. To spot the Triangulum Galaxy with the naked eye, you need a pure black sky and the eyes of an eagle. Nevertheless, it is easily visible through binoculars. Its oval disk is uniformly bright, although a slight excess of brightness towards the center betrays the presence of the bulge. Through a 300 to 400 millimeter telescope, we can easily observe its sumptuous spiral arms. The Triangulum Galaxy has particularly well-developed spiral arms, which appear spectacularly when viewed from the front. Yet it remains modest in comparison to the Milky Way and Andromeda galaxies, containing just 40 billion stars. Its very active arms are filled with regions of ionized gas, within which stars are born by the hundreds. The largest of these nebulae is NGC 604, the Triangulum Nebula. The Triangle Nebula, also known as NGC 604, spans 1,500 light-years and shines 6,000 times brighter than the Orion Nebula. Its immense tentacles of cold gas extend far beyond the visible disk. It was discovered by astronomer William Herschel on September 11, 1784. It lies nearly 3 million light-years from Earth. If it were at the same distance as the Orion Nebula, it would surpass the brilliance of Venus. It's an emission nebula with around 200 stars at its heart, with masses ranging from 15 to 60 solar masses. It is this same cluster of stars that irradiates the gas with energetic ultraviolet light, stripping electrons from atoms and producing the special glow of nebulae. A hot, sparse gas that emits X-rays fills the bubbles and cavities of the nebula. In 2018, astronomers discovered the first isolated neutron star outside the Milky Way. They detected it while observing the Small Magellanic Cloud, 200,000 light-years from our Sun, and more precisely, the remains of a supernova explosion that occurred there almost 2,000 years ago. This discovery was made possible by the use of advanced technology. By superimposing the X-rays captured by NASA's Chandra Space Telescope with the visible light observed by the MUSE instrument mounted on the European Southern Observatory's Very Large Telescope in Chile, they were able to immortalize the remains of this cataclysmic event. In this fabulous pocket of gas, named E0102 and known for almost 35 years, they detected a second ring of gas. This one, much smaller in size, shelters a bright spot in X-rays, a neutron star. While the scientists weren't too surprised by their find, they were stunned by its characteristics. The star is surrounded by two gaseous rings, both highly asymmetrical and extending at different speeds. The main ring expands at a speed of around 1,000 kilometers per second, or 620 miles per second, while the smaller ring, that mainly houses the star, has a speed of around 90 kilometers per second, or 56 miles per second. Scientists are comparing the energy spectrum of this neutron star with that of two other well-known stars in our galaxy. These are located in the supernova remnants Cassiopeia A in the constellation of the same name, and Puppis A in the constellation La Pope, also unaccompanied by another star. The star, detected only by its X-ray emissions, emits no radio emissions, pulsed or otherwise, indicating that its magnetic field is relatively weak. Of all the neutron stars discovered to date in the Milky Way, only 10 others display these same characteristics. But what is of great interest to astronomers is to understand how this neutron star came to be so far from the center of the main ring, and why it is moving, albeit slowly. Astrophysicists are studying two scenarios. It could be a displacement or deformation of the vast shock wave following a series of precise circumstances leading to this asymmetry. Alternatively, it could be that the neutron star, rather than the gas pocket, underwent a sudden impulse after a strong, asymmetric explosion, propelling it to its present position. In short, this first extragalactic neutron star, although in the spotlight, has not revealed all the secrets surrounding the circumstances of its violent death. Let's take a closer look at the puzzling characteristics of neutron stars. These stars are exceptionally small, averaging just 20 kilometers or 12 miles in diameter. On the other hand, their density is extraordinarily high, estimated at nearly 1,000 billion tons per liter. By way of comparison, if a teaspoon of this class of star were brought down to Earth, it would weigh over 1 billion tons. That's why they're often referred to as the relics of all extremes. What's more, these stars have a particularly intense magnetic field. It's usually on the order of 100 billion teslas, the tesla being one of the units of measurement for magnetic fields. When you put it like that, I imagine you'll find it hard to imagine what this represents, which is normal. In fact, the magnetic field of a neutron star can be described as immeasurable, especially when compared to that of our planet. The magnetic field of a neutron star is on average 100,000 billion times stronger than that of the Earth. There's another surprising feature of neutron stars. Their surfaces are particularly smooth, devoid of any irregularities. This is all the more disconcerting, given that such dense objects generally exhibit extraordinary gravitational attraction, which has repercussions on their surface relief. A study of the prominences observed on the surface of neutron stars estimates that their highest peaks are less than a millimeter high. Proportional to the Earth, the tops of these mountains would not exceed 50 centimeters or 20 inches. With such a force of gravity, it goes without saying that life is impossible on the surface of such an object, which, although it bears the name of a star, is technically no longer one. Indeed, to be scientifically perceived as a star, it would still have to be capable of stellar nucleosynthesis. However, neutron stars no longer have the necessary resources, and are therefore considered to be dying stars. By the way, what is a neutron star made of? Like all stars, it has a multi-layered structure with varying densities. Let's start by dissecting the star's anatomy, by looking at its atmosphere. This is reduced to a thin gaseous envelope whose thickness can be calculated in centimeters. This first layer, sometimes referred to as a gaseous ocean, has a temperature of several million degrees. Gravity at its surface is 10 billion times greater than that of the Sun. Oddly for a star, this first envelope conceals a solid surface. This is the outer crust, similar in composition to the interior of a white dwarf. Composed essentially of iron, it contains highly ionized atomic nuclei and free electrons. The iron atoms form a sort of latticework, creating a crystalline structure. As density increases, fusion reactions between atomic nucleus protons and free electrons create protons. The result is a transmutation of the basic atomic nuclei, which then resemble nickel, zinc, or krypton, depending on their density. When the density becomes too great, the nuclei, themselves too rich in neutrons, let some of the latter escape into what is known as the inner crust. The inner crust is made up mainly of extremely neutron-rich nuclei, bathed in a gas of neutrons and free electrons. The entire outer layer, divided as we've just seen into two zones, is around 1 kilometer or 0.6 miles thick. Below this limit, the density becomes so great that the atomic nuclei have completely disappeared, gradually dissolving. All that remains is a superfluid neutron soup, mixed with a small quantity of protons and electrons. This zone, approximately 10 kilometers or 6 miles in size, corresponds to the outer core of the neutron star. As the proton gas is superconducting, it must play a key role in the magnetic field. We're now at the heart of the neutron star, which could be in the form of a solid core. Of course, this is only a hypothesis, as this inner part of the star is not accessible. and therefore not observable. However, certain characteristics of this precise part of the star can be estimated, notably by studying its mass and/or radius. For example, a neutron star with a radius of around 10 kilometers or 6 miles and a mass equivalent to 1.4 times that of the Sun would have a solid inner core 1 kilometer or 0.6 miles in diameter, where the neutrons would form a crystalline structure. It remains to be seen how the particles that make up the neutrons and protons, namely the quarks, reorganize themselves into this extremely dense environment. Do they form hitherto unknown combinations? Another peculiarity of neutron stars is their rotation speed. They generally have a rotation period measured in seconds. For some, this speed can be 30 seconds, while the most excessive ones rotate in just 1/100th of a second. To explain this more or less frenetic pace, scientists suggest that the neutron star, at the moment of its creation, recovers the rotational motion that the star previously possessed, conserving its angular momentum, also known as angular momentum. As a result, as the neutron star contracts, becoming smaller and smaller in size, its rotational speed can only increase. Since a star's motion is proportional to its mass, radius, and angular velocity, what would happen if our Sun were to turn into a neutron star? Its current radius, around 700,000 kilometers, would be reduced to just 15 kilometers or 9 miles. With its mass maintained at the same level, i.e., nearly 333,000 terrestrial masses, our Sun's speed would increase exponentially. If it currently takes 25 days to complete one rotation, it would then rotate. Hold on to your hat, at 1,000 revolutions per second. Although this example is very explicit, it will never become reality. The Sun isn't massive enough to pretend to end its days as a neutron star. It will turn into a banal red giant and end up as a white dwarf. A priori, all neutron stars rotate rapidly after formation. However, this speed tends to decrease as the star's magnetic field dilutes its energy. As a result, an older neutron star will rotate more slowly than a newer one. It seems that the observed rate of decrease in rotation speed is relatively constant, and above all, insignificant. Depending on their behavior, neutron stars are classified into several subcategories. Some of these stars stand out in more or less extraordinary ways. Let's take a look at magnetars, some of the most exotic objects in the universe. Magnetars are characterized by extremely intense magnetic fields, producing high-energy electromagnetic radiation. In other words, X-rays and gamma rays. Apart from black holes, nothing in the cosmos generates such magnetic forces. The existence of magnetars was submitted in 1992 by two astronomers, Robert Duncan and Christopher Thompson. They established a relationship between the theory of intense magnetic fields and observations of gamma-ray sources. Observations of neutron stars with high Reynolds numbers, a dimensionless number used in fluid mechanics, demonstrated that these stars could generate extremely intense magnetic fields. While some neutron stars experience an increase in magnetic field strength as their rotational speed decreases, this is not the case for magnetars. This unusual characteristic is actually due to their very structure, and more specifically to their magnetosphere. But before we go any further, how is the magnetic field measured in general? Magnetic flux density is described in Tesla or Gauss units, with 1 Tesla unit corresponding to 10,000 Gauss units. The magnetic field at the Earth's surface corresponds to around 0.5 Gauss. Let's compare a few cosmic objects and their respective magnetic field strengths. The Sun's surface, depending on its activity, emits a magnetic field of around 3,000 Gauss. That of the supermassive black hole Sagittarius A is around 100,000 Gauss. That of the surface of a white dwarf is estimated at 1 million Gauss. Now imagine the strength of a magnetar's magnetic field, which reaches 100,000 billion Gauss at the very least. The magnetic field of any object is constantly changing. According to simulations, a magnetar's magnetic field could occasionally surge to 1 million billion Gauss. When it reaches a certain point between these two variables, it has a considerable impact on the star's outer layers. These, like a protective hyperdense crust as hard as or harder than diamond, see their structure deformed and fractured. When the magnetar's electromagnetic activity intensifies sufficiently, its neutron-based crust vibrates with such colossal intensity that it eventually shatters violently, just as the Earth's crust does during earthquakes. During these stellar tremors, which last between 0.1 and 3 seconds, and follow one another at an inordinate rate, X-rays and gamma rays are produced. These tremors, whose amplitude is estimated at 32 on the Richter scale, provoke veritable explosion eruptions that last a few days, or even weeks, before beginning a gradual decrease in intensity that can last several years before the star returns to its usual luminosity. Magnetars, described as the most powerful magnets in the universe, are the subject of much observation. A joint study by the Institute of High-Energy Physics of the Chinese Academy of Sciences and the Kepler Center for Particle Physics and Astrophysics at the University of Tübingen has discovered the magnetar with the strongest surface magnetic field ever observed in the cosmos. The record-holding object is an ultra-bright X-ray magnetar located in the constellation Cassiopeia, 24,000 light-years from Earth. It is the neutron star, Swift J0243, 6+6124, studied thanks to the Swift Multispectral Space Telescope in October 2017. Already known to scientists as the Milky Way's only X-ray source of so-called ultra-bright objects, it has now revealed some of its characteristics, and not the least. It belongs to an X-ray binary system of neutron stars, the other star being a pulsar, which unfortunately is being devoured by its magnetic companion. And with good reason. Its magnetic field is 1.6 billion Tesla, or 16,000 billion Gauss. That's around 5 billion times more intense than the solar magnetic field. Under the effect of this monstrous gravitational force, the gas from the neighboring star has no choice but to fall towards the neutron star, forming an accretion disk. As the plasma in the disk sinks into the magnetic lines until it reaches the surface of the neutron star, it ignites, releasing powerful X-rays. The latter, due to the star's rotation, manifest themselves as periodic X-ray pulsation signals. This is why this type of object is called an X-ray accretion pulsar. By carefully observing the spectrum of these X-rays, scientists discovered an electron-cyclotron absorption line and were able to directly measure the exceptional intensity of the magnetic field. This is the strongest magnetic field ever measured directly in the universe. To date, astronomers have recorded only 31 magnetars. These objects are as fascinating as they are rare. One of them, located around 15,000 light-years from Earth in the constellation Sagittarius, and discovered in March 2020 by the Swift Space Telescope, with rather unusual behavior, is intriguing to scientists. This is Swift J1818.0-1607. Everything suggests that this is the youngest magnetar of all. The primary star is thought to have exploded into a supernova just 240 years ago, around the time of the French Revolution. This conclusion was reached by Australian researchers, who observed the star 8 times between May and October 2020. Initially, they found that its radio emissions were similar to those of a pulsar, with varying intensities. Then these emissions began to behave strangely, sometimes pulsar-like, sometimes magnetar-like. This short-lived phenomenon had never been observed before with any other magnetar. What's more, J1818's magnetic axis is not aligned with its axis of rotation, its magnetic pole being located just below the equator in its southern hemisphere. But that's not the last strange fact. It turns out that on the 1st of August 2020, its radio beam moved briefly at the object's northern hemisphere, suggesting that this star's radio pulses originate from loops of magnetic field lines connecting two closely spaced poles. Typical neutron stars, like our Earth, have north and south poles opposite each other on either side of the object. The observation of this unusual behavior, coupled with the star's data, a mass twice that of the Sun, a diameter of 25 kilometers, and a rotation period of 1.36 seconds, will have enabled astronomers to determine its young age. More common are neutron stars that emit a beam of radiation along their magnetic axis periodically, in the form of very brief pulses. Because this radiation fluctuates or pulses rapidly, a pulsar looks more like a cosmic lighthouse, at least in appearance, than a lambda star or planet, which shine uninterruptedly. Incidentally, for a time, these radio waves, emitted at a rapid and regular rate, were mistaken for manifestations of extraterrestrial civilization. The interval between pulses can range from a few seconds to several milliseconds. If a pulsar also shines continuously, the radiation emitted by each of the two poles of this rapidly rotating star gives the impression of luminosity at regular intervals. Many pulsars cannot be observed from Earth. To be perceived, a pulsar's cone-shaped emission must be directed briefly in our direction. Some 2,700 pulsars have been identified to date, most of them in the Milky Way, some in its star clusters. Only a handful of pulsars have been detected in the Magellanic Clouds. Among the most famous pulsars, we can't ignore the very first to be discovered in 1967 by Jocelyn Bell. It's PSR B1919+21, located in the constellation Little Fox, which we've already observed earlier, just like the Crab pulsar. But let's take a closer look at the different types of pulsar, whose characteristics depend largely on their environment and age. The most common are radio pulsars. These can only be detected in the radio range, thanks to their intense pulsed emission. This is why we no longer speak of stars in the strict sense of the term, but of compact radio sources. X-ray pulsars, on the other hand, are detected by their X-ray emission. This X-ray emission is not related to the surface emission, which is nevertheless very hot, at least several million Kelvin, but is generally the result of an energetic process triggered by the star's rapid rotation. A second theory suggests that these X-ray emissions are due to a colossal energy release, attributed to the accretion of matter from a second object, particularly in binary systems. Other pulsars, known as gamma-ray pulsars, emit, as you'd expect, gamma rays. Around 100 gamma-ray pulsars have been identified to date. Most objects of this type that evolve on their own are as rare as they are difficult to detect. They are usually found in binary systems. Isolated pulsars, whether X-ray or gamma-ray, are virtually all radio pulsars. Some X-ray pulsars are said to be anomalous, as they exhibit abnormally high X-ray emission, resulting in an extraordinarily strong magnetic field. What's more, compared with other pulsars, they have a very long rotation period, of the order of 6 to 12 seconds. They also undergo a very rapid deceleration phase, meaning they are probably very young objects, potentially due to their extreme magnetic field. In contrast, some pulsars have prodigious rotation periods, ranging from 1 to 10 milliseconds. These are the millisecond pulsars, sometimes referred to as recycled pulsars. Their magnetic field is one of the weakest, although close to 100 million Gauss. Often orbiting a companion star or white dwarf, millisecond pulsars are very old. Last but not least, magnetars, the objects with unparalleled magnetic field strengths that we described earlier, are also a type of pulsar. Their disconcerting properties have yet to be fully explained. Are they singular objects, or are they just a temporary but usual phase in the evolution of pulsars? Understanding the stages through which stars pass also means being able to estimate their age. But how do scientists go about giving pulsars even an approximate date of birth? As we've just seen, pulsars rotate rapidly on themselves. Knowing that a pulsar's speed of rotation decreases over time due to its electromagnetic radiation, scientists are able to calculate the object's approximate age. Another method is to estimate the pulsar's kinematic age. In this case, after studying the object's immediate environment and defining the location of the supernova, researchers determined the time it took for the object to reach its current position. Many neutron stars have astonishing properties. We've already discussed Swift J818, which turns out to be a magnetar behaving like a pulsar, whose estimated age of just 240 years makes it the youngest pulsar yet discovered in the galaxy. But another pulsar is challenging astrophysicists with its strange behavior. PSR J0901-4046, also discovered in 2020, was detected after one of its pulses was picked up by the Meerkat radio telescope in South Africa. Because of its unusual behavior for a pulsar, it has long remained discrete. Unlike other stars in its class which rotate at very fast, even dizzying speeds, this one takes an inconceivably slow 75.88 seconds to complete one revolution. The slowest pulsar observed until this discovery completed a revolution in 23.5 seconds. For the researchers, this excessive slowness is more than a little disconcerting, especially as they thought that the radio emissions of neutron stars were a direct consequence of their rapid rotation. Another phenomenon makes this star totally baffling. It emits 7 different types of pulse, each with a different evolutionary history. Astronomers studying this type of star still have countless data to interpret, which should enable them to understand how they form and how they evolve. Above all, this latest find suggests that many stars like this slow pulsar are still hidden in our galaxy. As you know, in the cosmos, stars sometimes come very close together, forming binary systems. Some of these are natural laboratories for studying high-energy physics, general relativity, and stellar evolution. These are X-ray binary stars. These systems are composed of 2 different stars. One is an ordinary star, similar to the Sun, and the other is a neutron star, or in some cases a black hole. The neutron star or black hole, formed in the aftermath of a supernova, gravitationally attracts matter from its companion star, resulting in intense X-ray emissions. The material falling towards the neutron star forms a compact disk, from which friction generates such heat that a plasma is created, hot and shining in the X-ray range. 2 main types of X-ray binary star have been described. There are transient sources and persistent sources. The former are those that exhibit significant variations in luminosity, while the latter are stable, at least from the point of view of light emission. One of the most extensively studied X-ray binary stars is Her-X1. Located in the constellation of Hercules, it is composed of a normal A-type star and a 1.5 solar mass neutron star. The latter gravitationally attracts matter from its companion, forming the inevitable accretion disk that emits X-rays. These very intense rays vary according to several time periods. Because of its rotation, the star pulses with a period of 1.24 seconds. It eclipses every 1.7 days, according to the period of the binary orbit. More importantly, Her-X1's disk wobbles every 35 days, its line moving up and down as it rotates. The accretion disk of this neutron star thus has this strange feature. It wobbles as it rotates, influenced by winds within the disk. The study of disk winds fascinates scientists, who remain unsure of their origin. Is it the object's intense magnetic field that breaks up the disk before expelling some of the material outwards in the form of a wind? Or is it the radiation from the neutron star that heats up the surface of the disk, evaporating some of it and sending it flying away like white-hot gusts? Astronomers are working hard to determine the origin of these winds and to understand how they influence their environment. The majority of neutron stars observed to date are part of a binary system. In most cases, their companion is a main sequence star, a white dwarf, a red giant, or even another neutron star. Scientists also suggest that a neutron star could just as well be in close proximity to a black hole. Should such a discovery ever be made, it would be a major breakthrough for astrophysics. In the course of their many observations, radio astronomers at the Parkes Observatory in Australia detected an unusual binary system in May 2003. This relatively close system, located in the constellation of Pope and only 2,400 light-years from Earth, consists of two stars, which up to now has been nothing out of the ordinary. However, in-depth study of this system, named PSR J0737-3039, has revealed two equally sensational features. On the one hand, this system is made up of two pulsars of at least 1.4 solar masses each, a feature that has never been observed in any other system. Secondly, these two components orbit each other at an extremely short distance, estimated at twice the distance separating the Earth from the Moon. In short, these two pulsars, which take it in turns to eclipse each other, remain within a cosmic handkerchief the size of our Sun. These observations were greatly facilitated by the fact that the system's orbital inclination is practically 90 degrees to the Earth, showing us its edge. When the first pulsar is detected, its signal shows a modulation with a period of 2.45 hours. For the researchers, this Doppler effect means that a companion is evolving alongside the pulsar under study, at a relatively short distance. This fact is confirmed by the next observation, which describes the two stars as pulsars, the first with an intrinsic rotation period of 23 milliseconds, the second 1,000 times slower, turning on itself in 2.8 seconds. This duo have what it takes to put Einstein's famous theory of general relativity into practice. According to this theory, orbital motion can generate a deformation of space-time, causing the axis of rotation of one of the two components of a binary system to oscillate, a movement known as precession. After 16 years of remarkably precise observations, the measurement of precession analyzed corresponds to the estimates delivered by the equations of Einstein's theory. Predictions of the energy loss associated with gravitational waves have similarly matched the theory. Based on these data, scientists estimate that the common orbit of the two pulsars is shortening by 7 millimeters per day, leading to an inevitable merger, which is expected to occur in around 85 million years. Neutron stars never cease to amaze anyone interested in them. Would you believe me if I told you that such stars host one or more planets? In 1992, the first planet, or rather pulsar planets, were identified by the Arecibo radio telescope on the island of Puerto Rico, the largest single radio telescope in existence until 2016. This discovery was made possible by chronometry, which enables us to measure the minute variations in pulsar periodicity and deduce the main orbital parameters of the objects responsible. The first planetary system discovered evolves around a pulsar in the Virgo constellation, approximately 2,300 light-years from Earth. Named PSR B1257+12, it has been known since 2007 to contain not one, not two, but 3 exoplanets, with a 4th yet to be confirmed, as well as a potential asteroid belt. In 1992, this announcement sent shockwaves through the scientific community, which had thought that planets could only be found near main sequence stars. The closest planet to the pulsar, Dragar, has a mass 50 times less than that of the Earth, and orbits the pulsar in just over 25 days. It is the smallest planet ever observed in the universe. The second, named Poltergeist, is the most massive, with an estimated mass 4.3 times that of the Earth. Farther away, it orbits in 66.5 days. Relatively close to the third planet identified, Phobetor, it is in close gravitational interaction with the latter, which is about 3.9 times more massive than the Earth. Finally, a fourth object has been awaiting confirmation since 1996. An initial study, later refuted, suggested the presence of a planet 100 times more massive than the Earth, and some 40 astronomical units from its star. However, an object does appear to be located in this region of space, causing disturbances to the system under study. For some, it may not be a planet but an asteroid, or even a comet. The second planetary system of this type is located in the constellation Scorpio, more precisely in the globular cluster Messier 4. In this binary system, composed of the pulsar PSR B1612-26 of approximately 1.35 solar masses, and the white dwarf WD B1620-26 of approximately 0.34 solar masses, evolves the Genesis planet, more commonly known as Methuselah. This exoplanet, known as circumbinary because it orbits a binary star, is about 2.5 Jovian masses in size. It takes around 100 years to complete a full orbit around its 2 stars. But its most spectacular feature is its age. 3 times older than our planet Earth, it could be as much as 13 billion years old. It is undoubtedly the oldest planet ever observed in the history of astronomy. The study of this exoplanet is of great interest to scientists. Formed shortly after the Big Bang, it is thought to be composed essentially of chemical elements, resulting from the primordial nucleosynthesis that took place during the first instance of the universe's life. Neutron stars have extremely varied but relatively stable rotational speeds. There are a few exceptions, however, and they sometimes undergo punctual, and sometimes sudden accelerations. Astrophysicists call this phenomenon a glitch. This strange behavior is regularly observed in a neutron star just under 1,000 light-years from Earth. The Vela pulsar, visible in the southern sky, undergoes a glitch approximately every 3 years. Since this rotation anomaly seems to affect only a small population of pulsars, around 5% of them, the Vela pulsar, which experiences this problem with regularity, is particularly popular with glitch hunters. Observing these anomalies has enabled researchers to learn more about the star's composition. They found that at the moment of the glitch, the star began to rotate at a higher speed than previously observed, before slowing down to its cruising speed. They then deduced that the pulsar's center is actually made up of 3 components, one of which is a superfluid neutron soup located beneath the star's crust. Displacements within this hypothetical superfluid core would cause the famous starquake. When this neutron soup collides with the rigid outer crust, the celestial body is accelerated. Then, when a second mass of superfluid from the core hits the first wave, the star's rotation slows down. But these exciting observations raised a new mystery when it was observed that just before the glitch, the neutron star seemed to experience a slight slowdown before regaining speed. As yet, no explanation has been put forward, especially as there is no evidence that this phenomenon is related to the cause of the glitch itself. To understand the inner workings of such a celestial object, we must also consider its formation process. Neutron stars are among the densest celestial bodies in the universe, but knowing that they are merely the remnants of a dead star makes them all the more fascinating. Considered to be the little sisters of black holes, neutron stars can only form from certain stars, which must be particularly massive to make their final bow in a cataclysmic fireworks display known as a supernova. A star at the end of its life, over 10 solar masses, has a great chance of a second life as a neutron star. In other words, a dead star core. It all starts when a massive star reaches the end of its life, having burned all its fuel for the thermonuclear reaction. Some expand into peaceful red giants, but the most massive collapse in on themselves, exploding into a supernova. In this stellar disaster, the outer gaseous layers of the star are expelled into sidereal space. All that remains is the star's core, which no longer has enough energy to sustain the gravitational force. If its mass is less than 1.4 solar masses, it will take the form of a white dwarf. But in our case, its core, between 1.4 and 5.8 solar masses, generates energy in excess of the Chandrasekhar limit. As a result, electrons collide with protons, creating neutrons. The degenerate star eventually stabilizes. The remaining compact residue is then called a neutron star, with an average density corresponding to around 1,000,000 billion times that of water. Neutron stars are therefore born during explosive supernovae. While their future seems rather peaceful once the storm has passed, some of them experience other equally catastrophic events, notably stellar collisions. On August 17, 2017, Canadian astronomers were lucky enough to witness one of the most sought-after events in astrophysics, the explosive merger between two neutron stars. The two stars, located approximately 130 million light-years from Earth in the constellation Hydra, orbited each other at an ever-increasing speed, distorting the surrounding space-time, until the inevitable happened. The two massive stars collided and merged, triggering a gigantic explosion, which, due to its remoteness, could only be observed on this particular day in 2017. The event was first picked up by the LIGO and Virgo gravitational wave detectors in the USA and Italy respectively, and 2 seconds later, NASA's Fermi telescope detected a sudden burst of gamma radiation. For scientists, these two near-simultaneous observations led to a major discovery. For the first time, they were able to observe gravitational waves emitted, not by the merging of two black holes, but by the merging of two neutron stars. The signal detected proved to be much longer than in the case of black hole mergers, around 100 seconds versus a fraction of a second. Their second discovery was that this source of gravitational waves emitted light, which was observed for several weeks by 70 other ground and space-based observatories. This exceptional event, linked to two signals and named GW170817, became the first example of multi-messenger astronomy. For the first time in the history of astrophysics, such a cosmic event could be observed and confirmed using gravitational and electromagnetic waves. Because of its intensity, the explosion was catalogued as a kilonova, the first to have been the subject of real observations. Subsequently, scientists discovered that the new shape created by this fusion between the two neutron stars was, to their great surprise, perfectly spherical, as previous stellar explosion models had suggested a flattened, asymmetrical shape. The observation of this kilonova thus demonstrated that the theories and simulations carried out over the previous 25 years concerning these massive explosions were inaccurate. The error was attributed to the underestimated force of the explosions. Indeed, it was subsequently demonstrated that during the fusion process, the two neutron stars become part stellar giant before gravity causes them to collapse in on themselves. In this short space of time, colossal energy is released by radioactive decay in the star's core, allowing the explosion cloud to take on this unexpected spherical shape. Apart from the space-time undulations observed during this cataclysmic merger between two neutron stars, astrophysicists have made another discovery that should leave you dreaming. The collision of these two exotic stars has finally allowed them to solve the age-old riddle of how elements heavier than iron are synthesized in the universe. Remember, the heaviest element a star seems capable of creating is iron. Yet the cosmos is home to countless small, insignificant objects, at least at first glance, containing much heavier metals, such as silver, gold, and platinum. According to Enrico Ramirez Ruiz of the University of California at Santa Cruz, kilonovae, resulting from the fusion of two neutron stars, could well be the origin of an alchemy that creates these rare metals. According to the scientist, large quantities of neutrons are expelled during the cataclysm. These suddenly accumulate on neighboring heavy nuclei, forming heavier elements in a phenomenon known as the R process, or fast neutron capture. A single collision of this type could generate a colossal quantity of gold, equivalent to, hold on to your hat, a mass comparable to that of Jupiter. I leave it to you to imagine the enormous quantities of these singular atoms that could then sail with the cosmic tides in certain regions of space. As for the gold present on our Earth, it corresponds to the remnants of original gold atoms captured by our planet at the time of its formation, or deposited by asteroids that crashed into its crust. Other mergers between massive objects have been studied, notably that of two black holes whose gravitational waves were observed on September 14, 2015, thanks to the LIGO-Virgo collaboration, confirming the vibrations of space-time predicted 100 years earlier by Albert Einstein. Numerous other similar events have been detected. However, one scenario was missing, that of a mixed collision involving a neutron star and a black hole. Now, in January 2020, astrophysicists were fortunate enough to detect, just 10 days apart, two distinct signals corresponding to this precise pattern of mixed fusion. Again, thanks to the collaboration of LIGO and Virgo, but also Kagra, the Japanese gravitational wave detector, unusual gravitational wave events were recorded. On January 5, 2020, the signal name GW200105 came from a region of space around 900 million light-years from Earth, followed on the following January 15th by the signal named GW200115, a billion light-years away. Both turned out to be the result of collisions involving a large and a smaller mass, corresponding in both cases to a black hole violently absorbing a neutron star. This extremely rare phenomenon confirmed that beyond theory, a merger of this type could indeed occur. It also led to the conclusion that the neutron star, although highly massive, had been literally swallowed up by the black hole, which made short work of it without leaving the slightest crumb. Now we need to know the history of these two distinct, relatively massive objects. Did they originate from a pair of stars, one of which at the end of its life mutated into a black hole before engulfing its neighbor? Or did these two objects, originating in neighboring regions, eventually see their paths cross until the final explosive encounter? But let's return to a less chaotic region of space. I suggest you discover the neutron stars closest to our Earth. Known as the Magnificent Seven or the Seven Mercenaries, they were all discovered by the Rosat satellite, a German space telescope designed in the 1990s to observe low-energy soft X-rays. The first of these stars identified in 1992 was confirmed as a neutron star in 1996, followed by the other six. Located just 390 to 1,630 light-years from Earth, these stars generate powerful magnetic fields, and unlike their middle-aged counterparts, seem to remain extraordinarily quiet, giving off soft X-rays and ultraviolet light. This group of stars is of great interest to astrophysicists. They provide an ideal laboratory for unraveling the mystery of dark matter. Never observed by scientists, we still know nothing about the properties of this matter, for which there is nevertheless substantial astronomical evidence of its existence. For now, science suggests that dark matter could be a stable, electrically neutral subatomic particle of unknown mass. This theoretical particle is incidentally called an axion. Scientists are therefore interested in the Magnificent Seven that emit soft X-rays. Relatively silent and very quiet, these stars represent a unique opportunity to search for small, unexpected bursts of other forms of light, which could be linked to the presence of axions. By interacting with the intense magnetic field enveloping the neutron star, these could be converted into photons, or high-energy X-rays, i.e., hard X-rays. So far, astronomers have revealed that 2 of the 7 stars emit significant amounts of hard X-rays, while the others seem to emit them in much less obvious ways and in varying quantities. This suggests that axions may be the source of these hard X-rays. However, these axions have not been observed. This is still only a hypothesis, which needs to be put into practice. In fact, many laboratories are trying to reproduce this scenario. Who knows? One day soon we'll be told we've solved the mystery of dark matter, not in space, but on Earth. Another fact about the Magnificent Seven cannot be overlooked. It turns out that these neutron stars would have an 8e companion. Discovered in 2007, this neutron star, located in the Little Dipper constellation, at an estimated distance of between 250 and 1,000 light-years, has been christened Calvera. Located outside the galactic plane, its configuration remains a mystery. It is one of the few neutron stars to evolve on its own, with no companions or supernova traces in its vicinity. Could it be the remnant of an exploded star in our galactic disk? Researchers don't yet have an answer, but say it's probably the closest neutron star to Earth known to date. Its proximity and very high X-ray luminosity make it a prime target for studying this type of unusual star. Numerous research programs are underway to determine whether it emits pulses, either in X-rays or in the radio spectrum. Some neutron stars display ever more extraordinary characteristics. This is particularly true of J0740 plus 6620, whose discovery in 2019 has unsettled American astronomers. This pulsar is so massive that scientists thought no such star could exist. This small neutron star, with a diameter of no more than 30 kilometers or 20 miles, single-handedly defies the laws of physics, boasting a mass of 2.3 solar masses, or 700,000 times that of our Earth. Its mass, calculated thanks to the presence of a white dwarf companion, is so great that the star should be in the process of collapsing into a galactic black hole of several billion solar masses. However, this is not the case. This neutron star, though microscopic on the cosmic scale, should enable researchers to study the limits of stellar mass and further unravel the laws of the universe. One of the most unusual neutron stars is J1008-57. This is an X-ray pulsar in the accretion phase, detected in 1993 by a NASA gamma-ray space observatory. Its strangeness lies in its surface magnetic field, which is the strongest ever detected. It is around 1 billion Tesla, tens of millions of times stronger than a magnetic field that can be created in a laboratory on Earth. This exceptional peculiarity was discovered in 2020 by the Chinese Space Agency, which was quick to share this finding, challenging the known upper threshold of cyclotron resonant scattering. Neutron stars really are the stars of extremes. Although they are among the densest objects in the universe, one of them has once again stumped astronomers with its mass. It has not turned out to be monstrous, but on the contrary, has a value well below that predicted by theory. Named J1731-347, the star appears to be a neutron star in the afterglow of a supernova, 8,150 light-years away, with a mass of just 0.77 solar masses and an estimated radius of 10.4 kilometers or 6 miles. Until now, the lightest neutron star had a mass equivalent to 1.17 times that of the Sun. This once again challenges our understanding of stellar physics. Scientists are still trying to work out whether this is indeed an extremely light neutron star or a star of quarks. If the former, how could it have formed? Could a large part of its initial mass have been extracted from the core during the explosion due to the presence of its companion? Or could this star actually be a strange star, that hypothetical type of star, very dense and composed essentially of strange quarks of unknown composition? If so, it would be the first star of this type to be discovered. Indeed, strange stars are only a theory at the moment, and would lie on the borderline between a neutron star and a black hole. Finally, we can't look at neutron stars without considering the case of Betelgeuse, the well-known star in the Orion constellation that forms part of the famous Winter Triangle alongside Sirius and Procyon. Admittedly, it's just a red supergiant with an estimated mass of 15 solar masses. But this dying star, located just 530 light-years from our Sun, whose size is equivalent to 700 times our Sun, and whose luminosity places it 10e position after our Sun in the night sky, has been arousing the curiosity of astronomers for many years. It could well be nearing the end of its explosive life. What's more, a significant drop in its brightness was noted at the end of 2019, lasting several months before it returned to its previous appearance. While not all scientists agree on the reasons for this punctual dimming, the fact remains that the star goes through pulsating phases during which its size and luminosity fluctuate. Betelgeuse seems to be showing warning signs that the supernova that will give it the final coup de grace may be just around the corner on a human scale. For some astronomers, Betelgeuse's core must be in the final stages of carbon fusion. Given that this stellar explosion, which must be visible even in broad daylight, will take 530 years to be observable from Earth, it remains to be seen whether we will have the opportunity to admire it in our lifetime. Our neighbor Mars has two moons, Phobos and Deimos. These two moons are small bodies orbiting a few thousand kilometers from the red planet. Subject to the tidal forces of Mars, they rotate synchronously, meaning they always face the same direction as the planet. Their orbits evolve over time. Phobos moves closer to Mars, while Deimos moves further away. Let's continue moving through the solar system away from Earth. Neighboring Mars, the gas giant Jupiter is the planet with the most moons, with 92 confirmed satellites. Io, Europa, Ganymede, and Callisto, Jupiter's 4 largest satellites, are called Galilean satellites as they were discovered by Galileo in 1610. In fact, they were the first moons to be discovered after our own. Saturn is the second planet with the most moons, with 144 confirmed satellites, of which 66 have been given official numbers and 63 their own names. Saturn's 2 best-known moons are Enceladus and Titan, which we'll explore later in this trip. After Saturn comes the planet Uranus. 4 times larger than the Earth, it is the 3rd largest planet in the solar system after Saturn. Along with Neptune, it is one of the 2 icy planets in our solar system. Uranus has 27 moons. The first 2 satellites of Uranus to be discovered, in 1787, Titania and Oberon, take their names from Shakespeare's play. Titania is the largest satellite of Uranus and the 8th largest in the solar system. Neptune has 14 confirmed satellites, the largest and first to be discovered in 1846 being Triton. Pluto, demoted to dwarf planet status in 2006, is part of a double system with Charon, one of its satellites. Pluto's 4 other satellites are Styx, Nix, Kerberos, and Hydra. Let's turn first to Jupiter, the largest planet in our solar system, but also the one with the most moons. Jupiter is the 5th planet in the solar system in order of distance from the Sun, from which it is 779 million kilometers, or 485 million miles on average. This gas giant is the largest planet in size and mass, ahead of its neighbor Saturn. Its average radius is 69,911 kilometers, or 43,500 miles, or 11 times that of the Earth, and its mass is 318 times that of our planet. In fact, Jupiter is so huge that it has been visible to the naked eye since prehistoric times. After the Sun, Moon, and Venus, Jupiter is the 4th brightest object in our night sky. In fact, its great luminosity is the origin of its name, which comes from the Roman god Jupiter, master of the other gods. Composed mainly of hydrogen and helium, Jupiter's composition is similar to that of the Sun. Although it has a rocky core of heavy elements, it has no solid surface. In its atmosphere, several elements have been detected, including methane, ammonia, sulfur and nitrogen compounds, and water ice. Jupiter, its 92 moons and rings, are known as the Jovian system. But the giant planet's influence extends far beyond the Jovian system. This influence is exerted, for example, on Jupiter's Trojan asteroids, a group of asteroids that share its orbit around the Sun. The first space probe to fly over Jupiter was the American Pioneer 10 in 1973. Until 1979, the planet was explored by Pioneer and Voyager 1 probes. Then between 1995 and 2003, the Galileo probe orbited Jupiter, followed by the Juno orbiter in 2016. Juno is currently still orbiting Jupiter, until at least 2025. Unfortunately, we've long known that the chances of Jupiter harboring life are remote. Not only does Jupiter have no solid surface, but its presence and internal temperatures are extreme. No biological object could survive on this type of planet. So why do Jupiter exploration programs continue to fuel the hopes of alien hunters? Because Jupiter has 92 moons, 4 of which could potentially be habitable. These are the famous Galilean moons. That Jupiter's moons are habitable is hardly surprising. The Jovian system is often compared to a miniature version of the solar system. Jupiter accumulated so much thermal energy due to gravitational contraction during its formation that it now releases more thermal energy than it receives from the Sun. It could therefore act for its moons like the Sun for the planets in our solar system. Jupiter's 4 Galilean moons were discovered by Galileo in 1610. The Italian astronomer gave his name to these satellites, although they may have been observed earlier by the Chinese astronomer Gan Day in 362 BC. Between the end of the 19th century and the early 1650s, 8 other satellites of Jupiter were discovered: Amalthea, Himalaya, Elara, Pasiphae, Sinope, Lysithea, Carme, and Anakie. Leda and Themisto were discovered in the 1970s. So, before the arrival of space probes on Jupiter, 14 satellites of the Jovian system were already known. In 1979, 3 more moons were discovered. The number of known satellites was increased to 63 by new observations at the turn of the century. And from 2010 onwards, new observations expanded the catalog of Jovian moons. The last 15 known satellites were discovered very recently, in 2022 and 2023. So it's possible that more will be found in the years to come. It's true that at first glance, Jupiter's moons don't seem very hospitable. They are far from the Sun, almost all encased in ice, and their atmosphere is very sparse. But their observation has revealed some fascinating facts that are well worth investigating. Galilean moons are likely to conceal liquid oceans beneath their icy crusts, and liquid water means the development of biological organisms. What's more, the thick ice crust could provide good protection against radiation and meteorites, as well as thermal insulation conducive to the development of life, a bit like our atmosphere on Earth. But let's take a closer look at these moons to find out more about their potential for harboring life. Fasten your seatbelts as we explore Jupiter's 4 Galilean moons: Io, Europa, Ganymede, and Callisto. Let's start with Io, perhaps the moon in the Jovian system least likely to harbor extraterrestrial life. You'll soon see why. Io is also called Jupiter 1, perhaps because it is the satellite of Jupiter whose orbit is closest to the gas giant. Its period of revolution is just 42 hours. It is Jupiter's third largest moon and the fourth largest in the solar system. But it's also the densest and most geologically active, with over 400 active volcanoes. The fact that Io is so volcanically active first surprised scientists. When the Voyager probe flew over Io, it detected something unexpected on its surface: hundreds of giant active volcanoes. Other probes have since spotted huge lakes of molten lava. These discoveries are quite astonishing, as volcanic activity on Earth is fueled by the heat of the Earth's core. However, Io is so small that it must have cooled down completely billions of years ago. The only possible explanation was that Io certainly conceals in its core another source of energy that can continuously fuel this volcanic activity. The observation of volcanoes on Earth and the data collected on Io enabled us to imagine what life would be like on this moon. Living on Io would mean living in an extremely hostile environment, very cold or very hot, with no atmosphere. If you were to walk on Io, you would bounce slightly because the gravity on Io is the same as on the moon, 6 times less than on Earth. You could walk through black lava fields and witness phenomenal volcanic eruptions. Because on Io, eruptions are extremely spectacular. The gases released by the lava project clouds into the interstellar void. On its way to Pluto, NASA's New Horizons probe passed close to Jupiter in March 2007 and photographed an impressive volcanic eruption on Io. The eruption was that of the Tvashter volcano. The images taken at the time by the probe's high-resolution telescopic camera are impressive. They show a plume over 300 kilometers, or 185 miles high, rising in Io's northern hemisphere, and then raining down on the surface. These images provide researchers with proof that volcanic eruptions on Io are violent and powerful. But what could be generating so much energy in the heart of this frozen moon? In fact, this intense geological activity is the result of tidal heating. This heating is due to the friction generated inside the moon by its gravitational interactions with Jupiter and 2 other Galilean satellites, Europa and Ganymede, with which it is in orbital resonance. In other words, with each of its revolutions in its elliptical orbit around Jupiter, Io is buffeted by the gas giant's gravitational forces. When it reaches the point in its orbit closest to Jupiter, it undergoes a deformation of over 100 meters or 330 feet. Imagine this over billions of years, and you can see how intense friction could have arisen within this small moon. It's a bit like twisting and unfolding a piece of metal. It will eventually heat up. It's the same for Io. These movements and deformations have created an alternative energy source at the heart of Io, capable, in theory, of promoting life. Remember, life needs 3 elements to emerge, including a source of energy. With these discoveries, researchers realized that they had to stop believing that habitable celestial objects had to resemble the Earth in every way, and that habitable zones were necessarily dependent on the Sun. The perimeter, likely to harbor life, extended from the Earth to the farthest reaches of the solar system. However, the probability of life existing on Io remains very low. Yes, Io has an energy source. Yes, Io could contain the chemical elements that make up life, which would have been disseminated like on Earth by comets and asteroids billions of years ago. But researchers have never succeeded in finding the third element necessary for the emergence of life: liquid water or its equivalent. Why couldn't there be liquid water under Io's volcanic crust? Because, unlike other moons, Io is not made of water ice, but of silicate rock, surrounding a molten iron or pyrite core. Although the chances of Io harboring any form of life are slim to none, researchers are nonetheless interested in this moon for its intense volcanic activity. The interest of these volcanoes is not only scientific, but also aesthetic, as the images of this moon are magnificent. Io's volcanoes produce plumes of sulfur and sulfur dioxide, which, after rising several hundred meters, rain down and cover the moon's vast plains with a frosty layer of material. This material also forms a thin layer of atmosphere. Lava flows can extend over 500 kilometers or 310 miles in length. The moon's surface is constantly changing, taking on shades of yellow, red, green, white, and black. Io's surface is also dotted with over 100 mountains, the result of tectonic phenomena on the moon's silicate crust. Some of these mountains rise very high, even higher than Mount Everest, even though Io's radius is 3.5 times smaller than Earth's. Impressive, isn't it? There's no doubt that researchers won't be giving up their observations of this moon, which still conceals so many mysteries other than that of life. Let's continue our exploration of the Galilean moons with Europa, or Jupiter 2, the sixth closest moon to Jupiter. Europa has a period of revolution of 85 hours. With a diameter of 3,122 kilometers, or 1,900 miles, it's the smallest of the Galilean moons, but the sixth largest in our solar system. It's also the most interesting in the search for extraterrestrial life. In fact, according to researchers, it's the one where life is most likely to be found. Let's take a closer look at this mysterious moon. Europa has been flown over 12 times by NASA's unmanned spacecraft Galileo. Virtually all our data on Europa was collected by this probe. Europa is barely smaller than our moon. It consists mainly of silicate rock, with a crust of water ice and a core, probably of iron and nickel. It has a very thin atmosphere composed mainly of oxygen. Its temperature at the equator is minus 183 degrees Celsius or minus 297 degrees Fahrenheit, and its temperature at the poles can drop to minus 223 degrees Celsius or minus 370 degrees Fahrenheit. Unlike Io or our moon, its surface is free of craters, making Europa the smoothest surface celestial object in the solar system. Its surface is relatively young, estimated to be just 100 million years old. Locked in by Jupiter's tides, Europa rotates synchronously around the gas giant, so it always presents the same face. Small deviations in its rotation have been observed. All these observations could mean that there is a liquid layer between the surprisingly smooth surface of the small moon and its rocky core. This hypothesis was confirmed by the Galileo probe's studies of the satellite's interaction with Jupiter's magnetic field. While there are no impact craters on Europa's surface, there are glacial striations and fissures known as lineae. These crevices have been analyzed by the Galileo probe. The analyses show that in the past, the satellite's crust moved 80 degrees in relation to its interior, which would have been impossible without a liquid layer beneath the surface. What's more, as the Galileo probe got closer to Europa, it was able to observe these cracks more closely. The data collected suggests that in some places the ice cracked, then a trench formed, and a material filled the empty cracks and froze, allowing the parts to be welded back together. It's a bit like kintsugi. The probe also showed huge fields of jagged ice, as if the ice had melted and then roughly reconstituted itself, reminiscent of the ice that covers our oceans on Earth. The Galileo probe also took measurements of Europa's magnetic field. Analyses revealed the presence of an electric current that could correspond to that of a salty ocean of liquid water. According to the prevailing model, Europa's slightly eccentric orbit, maintained by its orbital resonance with Io and Ganymede, causes a tidal heating effect, allowing the ocean to remain liquid. This leads to a movement of ice, similar to plate tectonics, the first time this mechanism has been found anywhere other than on Earth. Like Io, Europa is therefore heated by internal friction due to its interaction with the gravitational fields of Jupiter and the satellites with which it is in orbital resonance. This may explain the jagged ice, which appears to have been melted and then refrozen. These interactions would cause powerful tidal waves in its inner ocean, further raising the temperatures inside the satellite. All this makes the presence of a liquid ocean possible. According to the researchers, this internal ocean could be as deep as 100 kilometers or 60 miles, with a volume twice that of our oceans on Earth, nicknamed the Blue Planet. Europa thus appears very different from its sister moon Io. It is covered by an exceptionally smooth and clean layer of ice. The highest features of its relief rise only a few hundred meters above the surface, a completely different landscape from Io's high mountains. The thickness of the ice crust varies between 10 and 30 kilometers, or 20 miles. Europa's surface is striated by a network of long, deep fissures. Some of these cracks may be reaching the groundwater layer. If this is the case, the ice that covers the bottom of the crevices provides valuable material for studying Europa's interior composition. Europa's geysers occur regularly throughout the moon's orbit, but are most frequent when the moon is furthest from Jupiter. This is because Jupiter's tidal forces are weaker when the moon is further away. These tidal forces are responsible for the formation of geysers, forcing water from the underground ocean towards the surface. These geysers, detected by the Hubble telescope, can reach up to 200 kilometers or 125 miles in height. These giant jets are made up of water vapor, a surprisingly clean form of water. It's possible that this water comes from Europa's underground ocean, or from giant lakes hidden beneath the ice crust. These are invaluable to scientists, as they would enable them to detect traces of life without having to use a lander. For the moment, nothing is certain. In the absence of concrete data, the composition of Europa's ice crust is currently estimated on the basis of one of its largest craters. Spectral analysis of the craters reveals compounds of magnesium, sulfur, iron, and hydrogen peroxide. Conclusion: there is certainly a wide diversity of minerals in the satellite's hidden hydrosphere. It's also important to point out that Europa's atmosphere contains oxygen, which is formed when icy water is broken down by UV rays. But Europa's gaseous envelope remains 1 trillion times sparser than that of the Earth. In any case, according to some calculations, the oxygen concentration in Europa's oceans could be sufficient to sustain single-cell aerobic life. Aerobicity is the ability of an organism or microorganism to thrive in ambient air using oxygen. Europa has liquid water and the building blocks of life. We still need a third element to affirm that life can develop there, a source of energy. And it does have a source of energy, undersea volcanoes that saturate the water with sulfur and iron oxides. Some researchers even claim that there could be multicellular organisms in the European Ocean, but this hypothesis is still premature. In any case, all we know is that we can't rule out the possibility of primitive life on this mysterious moon of Jupiter. Faced with all these possibilities, researchers are wondering whether it is really possible for a form of life to survive in this type of environment, namely, a cold liquid ocean enclosed beneath kilometers of ice, with no access to the sun's energy and with underwater volcanic activity as its sole source of power. The answer could lie on Earth. Biologist Tim Schenck has explored the waters of our planet that bear the closest resemblance to the icy depths of the Jovian satellite. 320 kilometers or 200 miles from the North Pole, the biologist sent robots 3,600 meters or 12,000 feet deep beneath the Arctic ice sheet, where sunlight never breaks through. In other words, the robots were sent into an ultra-hostile environment, where temperature and pressure levels are extreme due to underwater volcanic activity. The aim? To understand what might be going on beneath Europa's ocean by observing the most hostile underwater environments on our planet. At depths of 3,600 meters or 12,000 feet in the heart of the Arctic Ocean, Tim Schenck's robots, unsurprisingly, collected evidence of a very hostile environment. Volcanic fissures spew water at 370 degrees Celsius or 698 degrees Fahrenheit, saturated with toxic chemical compounds such as hydrogen sulfide. This type of fissure is more than likely to be found in the depths of Europa's oceans. Surprising as it may seem, Tim Schenck has discovered living organisms around these cracks. These cracks are in fact lined with microbes for miles around, new forms of life that we never knew existed, but which are indeed living organisms. Even the polar oceans on Earth harbor microbial life, so why not on Europa? How do these microbes survive in such a hostile environment? Instead of using the sun's energy, they use sulfur, methane, and hydrogen as a source of chemical energy. The next step is to land a probe on Europa to verify the scientists' theories, but for that we'll have to wait a little longer. For one thing, the Moon is 628 million kilometers away. What's more, we'd have to build a robot capable of crossing kilometers of ice, then swimming in the icy water to collect data. This is already a complex task on Earth, so imagine it, over 600 million kilometers from our planet. Are moons that generate heat as they make their revolution, causing the ice to melt and underground oceans to form, ideal for the development of life? A far-fetched idea? Perhaps not, as Europa is not the only moon that could fit this model. Ganymede, or Jupiter 3, is the third Galilean satellite. Its orbit lasts about 7 Earth days. It is not only Jupiter's largest satellite, but also the largest in the entire solar system. In fact, it's the satellite that most closely resembles a planet. Its diameter is 5,268 kilometers, or 3,000 miles, or 8% larger than the planet Mercury, and 2% larger than Saturn's largest moon, Titan, which we'll study later. However, its mass is only 45% that of Mercury, as it is made up of equal amounts of water ice and silicate rocks, whereas Mercury is made up solely of rocks and metals. Ganymede is just over twice the size of our moon, and twice as heavy as our satellite. You can see it with the naked eye in our night sky. It's the only satellite in our solar system with a liquid metal core and its own magnetosphere. This magnetosphere was probably created by convection within the liquid iron core. Ganymede completes its orbit around Jupiter in 7 Earth days, around 1 million kilometers from the gas giant. Its orbit is slightly eccentric and inclined to Jupiter's equatorial plane. Its rotation is controlled by Jupiter's gravitational tidal effects, like Io and Europa, so it too is in synchronous rotation. When Ganymede makes one complete revolution around Jupiter, Europa makes 2 and Io 4. Ganymede is therefore in orbital resonance with the other 2 Galilean moons. Ganymede's atmosphere is thin and contains several elements: atomic oxygen, dioxygen, and possibly ozone, as well as atomic hydrogen in small proportions. Pioneer 10 was the first probe to take a close look at Ganymede. In the 1970s, the American probes Pioneer 10, Pioneer 11, and Voyager 1 and 2 provided some insight into Ganymede. Then, the Galileo probe refined some of the data we have on this Jovian satellite, thanks to 6 close flybys between 1996 and 2000. Thanks to Galileo's data, we were able to discover its underground ocean and magnetic field. Like Europa, Ganymede is thought to have an ocean under its surface ice, which could contain more water than all the oceans on our planet put together. 1/3 of the satellite's surface is covered by 4-billion-year-old impact craters, and 2/3 by lighter-colored regions cut by wide grooves. This relief is probably the result of tectonic activity, triggered by tidal heating, although for the moment it remains a mystery to scientists. Some researchers believe that Ganymede has an ocean sandwiched between 2 layers of ice, while others think that there are several layers of ocean separated by different layers of ice, a bit like a mill fuel of water and ice. Ganymede's magnetic field is due to its iron-rich liquid core. As the magnetosphere is essential to protect us from radiation coming from space, the existence of this magnetic field is an argument in favor of the presence of life on this moon. Ganymede's magnetic field produces polar auroras, as shown by images taken by the Hubble telescope in 1995. Another feature of this magnetic field is that it is contained within the larger magnetic field of Jupiter. Studies of Ganymede's magnetic field by the Galileo probe show that there could be a multi-layered salty ocean beneath the ice crust at a depth of at least 200 kilometers or 125 miles. Multi-layered because this ocean could have up to 4 layers, each with its own salinity and density. These 4 layers would be separated by ice. On the surface of Ganymede, Galileo's high-resolution spectroscope has revealed the presence of a large number of non-aqueous materials. These include carbon dioxide, sulfur dioxide, sulfuric acid, various organic compounds, magnesium sulfate, and sodium sulfate. These materials probably originate from Ganymede's subglacial ocean, although it is not yet known by what mechanisms these compounds could have reached the surface by penetrating the satellite's crust. Researchers believe that Ganymede may have formed by accretion, i.e., the progressive agglomeration of the gases and dust that surrounded Jupiter after its formation. The average surface temperature of Ganymede is minus 148 degrees Celsius or minus 234 degrees Fahrenheit. A decay process inside Ganymede would heat the satellite even more, so that the core would have an average temperature of 1200 to 1400 degrees Celsius or 2550 degrees Fahrenheit. The presence of oxygen in Ganymede's atmosphere is not in itself proof of the presence of life on this satellite, as molecular oxygen can result from the decomposition of water ice under UV light. During this process, hydrogen evaporates into space, and oxygen, a heavier element, is deposited on the surface. For the moment, nothing is certain, but Ganymede remains a moon to keep a close eye on in the quest for extraterrestrial life in our solar system. We're now going to explore Jupiter's last Galilean moon, Callisto. Callisto, or Jupiter 4, is the second largest Jovian moon after Ganymede and the third largest in the solar system. It is the Galilean moon furthest from Jupiter, and therefore the only one of the 4 not to be in orbital resonance. Like Ganymede, Callisto is thought to have formed by accretion from the disk of gas that surrounded Jupiter after its formation. With a diameter of 4,820 kilometers or 3,100 miles, Callisto is roughly the size of Mercury. This moon has a thick crust of ice, 80 to 150 kilometers deep. It is made up of roughly equal parts rock and ice. However, it has one major difference from Ganymede. It does not undergo tidal heating and is therefore only partially differentiated. In other words, it does contain layers at different densities, but not at full depth. According to data collected by the Galileo probe, Callisto may have a small silicate core and an ocean of liquid water more than 100 kilometers beneath its surface. As on Ganymede and Europa, this ocean could harbor life. Its depth is estimated at between 50 and 300 kilometers, depending on the model, and its temperature would be around minus 20 degrees Celsius or minus 4 degrees Fahrenheit. Because of the high pressure, the water in this ocean would remain liquid. But beneath this ocean probably lies a layer of ice 300 kilometers or 185 miles thick, and a core composed of ice and rock. Callisto's surface is old, heavily cratered, and shows no sign of tectonic activity. Because Callisto is further from Jupiter than the other Galilean moons, its surface is less affected by the gas giant's magnetosphere. Callisto is surrounded by a thin atmosphere composed mainly of carbon dioxide and probably molecular oxygen, as well as by an intense ionosphere. Explored on numerous occasions by space probes such as Pioneer 10 and 11, Galileo, and Cassini-Huygens, Callisto is often considered the most suitable body for a human base to explore the Jovian system. However, the likelihood of this satellite harboring any form of life is lower than for Europa or Ganymede. The impact of Jupiter's tides is not enough to properly deform the satellite, as Callisto is located too far from Jupiter. As a result, the satellite cannot draw much heat from the gas giant. What's more, Callisto is made up mainly of ice, whereas it would be preferable for water to be in contact with hard rock to be saturated with the elements necessary for the appearance of life. In fact, the low diversity of chemical compounds and low temperatures on this satellite considerably reduce the chances of life appearing and developing. But this possibility should not yet be totally ruled out. Unfortunately, no more is currently known about the possibility of extraterrestrial life on Jupiter's moons. These moons have been explored only briefly, by spacecraft en route to another destination. But more recently, projects dedicated to the study of Jupiter and its moons have emerged. NASA's Juno probe arrived in Jupiter's orbit in July 2016, and has since delivered extraordinary images of the gas giant. In July 2021, it moved on to study the Galilean moons. On September 29, 2022, it flew very close over the moon Europa, passing just 352 kilometers or 220 miles from its surface. This was only the third time a probe had flown over this satellite. The flyby enabled the probe to take photos of the moon, as well as samples, to be compared with Galileo data collected at the beginning of the century. On October 16, 2023, images of Io were revealed by the American probe, which passed within 11,645 kilometers, or 7,500 miles of the moon. The European Space Agency's JUICE project is also eagerly awaited. Its aim is to study Jupiter and the three Galilean moons that could harbor life: Ganymede, Europa, and Callisto. JUICE stands for Jupiter Icy Moons Explorer. The probe was launched on April 14, 2023, and is scheduled to arrive in orbit around Jupiter in 2031, after a 7.5-year journey. This positioning will enable it to fly repeatedly over the Galilean moons to collect data. Researchers have high hopes for this project, because if all goes well, it could considerably enrich our knowledge of Jupiter and its satellites. In December 2034, the probe will orbit Ganymede to study this satellite in greater depth, before completing its mission in September 2035. Another mission is being developed by NASA, this time to study the moon Europa in depth. This is Europa Clipper. This automatic probe should leave Earth in October 2024 and reach the Jovian system in April 2030. These projects are promising and should help us learn more about the presence or otherwise of highly resistant living organisms in the subterranean oceans of these moons. Researchers don't expect to find little green men on these satellites, but rather simple organisms like those found on Earth, at the bottom of the oceans near areas of volcanic activity. But it's a good start, since life on Earth probably evolved from these ultra-resistant microorganisms. Could there be other moons in our solar system with conditions similar to Europa, Ganymede, or Callisto, suitable for the appearance and development of life? The Cassini-Huygens space mission was designed to answer this question. Its objective? To explore the Saturnian system, i.e., the planet Saturn and its satellites, determine how Saturn's rings were formed, and inspect some of the giant planet's moons. This mission, developed by NASA with the participation of the European Space Agency and the Italian Space Agency, was launched on October 15, 1997, and ended on September 15, 2017. After flying past Jupiter on December 30, 2000, the probe was placed in orbit around Saturn on July 1, 2004. On January 14, 2005, the Huygens lander detached from the probe and landed on the surface of Titan, Saturn's largest moon, while the Cassini orbiter continued to collect data on Saturn and its satellites as they passed close to the gas giant's orbit. The mission was scheduled to last 4 years but was extended twice, ending on September 15, 2017. The Cassini orbiter was equipped with the most sophisticated instruments ever taken to the outer solar system: cameras, spectrometers. Particularly costly, this mission was a real success, as it provided scientists with a wealth of data on the Saturnian system, Saturn, its magnetosphere, its rings, Titan, and the other satellites of this giant planet. Thanks to the Cassini-Huygens space mission, Saturn's rings have been revealed in detail for the first time. These rings stretch for thousands of kilometers, yet in some places they are no thicker than a few dozen meters. The Cassini probe has confirmed that these rings are made up of billions of shiny particles of almost pure water ice. These particles vary enormously in size, from a speck of dust to a mountain. The data collected has also made it possible to date the rings. They were created less than 100 million years ago and should disappear in less than 100 million years. But above all, the Cassini-Huygens mission has also enabled us to refine our knowledge of Titan and to discover astonishing features of Saturn's other moons, notably Enceladus and its geysers, clues to an underground ocean that could perhaps harbor a form of life. In all, Saturn has 146 satellites, 144 of them confirmed. It also has more than 150 helices in its rings, which could be minor moons, i.e., particularly small natural satellites, At least 150 minor moons have been detected in Saturn's rings through the disturbances they create in their environment. But researchers suspect that this is only a small portion of the total population of these objects. Saturn's satellites vary in size from less than a kilometer in diameter to 5,149 kilometers or 3,200 miles in diameter for its largest satellite, Titan, which is larger than the planet Mercury. We'll now take a look at Saturn's two most notable satellites, Titan and Enceladus. Let's begin our journey into the heart of the Saturnian system by exploring Titan, the largest of Saturn's moons. Titan, or Saturn VI, is the second largest moon in the solar system after Ganymede. It was the first moon of Saturn to be discovered by Dutch astronomer Christian Huygens in 1655. One of Titan's special features is that it is the only known satellite to have a dense atmosphere. Its atmosphere is made up of 98.4% dinitrogen and 1.6% methane and ethane, and lies between 200 and 880 kilometers in altitude, i.e., almost 500 miles above sea level. To give you a point of comparison, on Earth, 99.99% of the mass of the atmosphere is less than 100 kilometers or 60 miles above sea level. It's also difficult to obtain a spectrum of Titan's surface, as its atmosphere is opaque over a wide range of wavelengths. Titan's atmosphere contains layers of opaque fog that block out most of the sun's light, so much so that the Huygens probe team described the process of photographing Titan's surface as photographing an asphalt-covered parking lot at dusk. The temperature of the atmosphere is around minus 180 degrees Celsius, or minus 292 degrees Fahrenheit, and reaches minus 200 degrees Celsius, or minus 328 degrees Fahrenheit, at the tropopause, at an altitude of 40 kilometers, or 25 miles. According to observations by the Voyager probes, the pressure at the satellite's surface exceeds 1.5 times that of the Earth. Titan is composed mainly of rock and frozen water. Its surface is geologically young, with a few mountains and cryovolcanoes, but overall, a relatively flat and smooth surface, with few impact craters. Winds and methane rains, which are frequent on Titan, create dunes and coastlines on the satellite's surface, just like on Earth. Titan also has seasons. When Cassini's Huygens module visited Titan in 2004, it detected elements of life in its atmosphere. But that's not all. As it flew over the moon, it detected something mysterious, partly hidden by the clouds gathering over its south pole, resembling a lake of water. Numerous flybys subsequently revealed the existence of hundreds of such lakes, scattered across the moon's north and south poles. What is the significance of these mysterious lakes? Could it be that, as on Earth, they are lakes of water with a rich ecosystem? This question has intrigued researchers, as Titan is the only known environment other than Earth to feature liquid expanses on its surface. But given Titan's surface temperature of minus 180 degrees Celsius or minus 290 degrees Fahrenheit on average, these lakes cannot be lakes of liquid water. After analyzing the infrared waves reflected by the lakes, the researchers concluded that they were in fact liquid methane and ethane at very low temperatures. On Earth, these elements are used as fuel in gaseous form. But on Titan, liquid methane digs valleys, forms clouds, and falls as rain. In fact, it behaves exactly like water on Earth. Researchers then wondered whether this methane could be conducive to the formation of life, allowing organic molecules to dissolve, mix, and interact, just like water on Earth. Our theory of life includes the need for a liquid element. On Earth, water enables organic molecules, the basic ingredients of life, to dissolve, assemble, and interact with each other to form larger, more complex molecules, destined to develop into living beings. But could another liquid do the trick? Could the building blocks of life dissolve in methane and give rise to life? Astrobiologist Chris McKay has attempted to answer this question. To do so, he used the elements detected in Titan's atmosphere by the Cassini mission and carried out a simulation. First, he reproduced the reaction that takes place on Titan to obtain the same organic material as in its atmosphere. Next, he recreated the lakes, detected by the Huygens module's radars, by filling a test tube with methane gas, which he cooled to minus 143 degrees Celsius or minus 225 degrees Fahrenheit using liquid nitrogen. The methane liquefied exactly as it does on Titan's icy surface. Chris McKay was thus able to obtain a miniature Titan lake in his test tube, namely, a bath of liquid methane with organic materials. The aim now is to find out whether these materials will dissolve to form more complex molecules and ultimately a new form of life. If these organic materials can dissolve, it means that the chemical processes necessary for life could exist on Titan, and on a larger scale, that they are capable of being triggered even in conditions of extreme cold and in liquids other than water. This would also mean that life has arisen twice under different conditions, and that it is therefore a natural process that can appear in other places. This would open up infinite possibilities. In any case, if there is life on Titan, it bears no resemblance to life on Earth. While we await the results of Chris McKay's experiment, other evidence of possible life on Saturn's satellite has been put forward. A team of researchers has identified a deficit of acetylene on Titan's surface. This molecule, which forms on the planet's surface, should be present in Titan's lakes, but has not yet been detected. According to Chris McKay, acetylene could indeed be the food of choice for hypothetical life based on liquid methane, but nothing is certain yet. The lack of acetylene could just as easily result from the action of sunlight or cosmic rays, which are capable of transforming acetylene into other, more complex molecules that no longer display its spectral signature. Whatever the case, researchers are still hopeful of finding some form of life on Titan. This moon of Saturn closely resembles a primitive Earth, albeit at a lower temperature in many respects. Its liquids on and below the surface, its thick atmosphere of diazote, Titan could well contain extraterrestrial microbial life, or at least a prebiotic natural environment rich in complex organic chemistry. Another of Saturn's moons has attracted the curiosity of researchers, Enceladus. On the face of it, this satellite isn't the most interesting. It's only Saturn's 6th in size and 14th in distance. But since the Voyager 2 and Cassini-Huygens missions, researchers have been taking a close interest in this small moon, which boasts some astonishing features. Enceladus is a real mystery, very different from Saturn's other moons in its appearance and shimmering white surface. It displays a complex geological activity, difficult to explain for such a small body. Indeed, Enceladus measures only 500 kilometers or 310 miles in diameter on average. However, the Cassini probe has spotted cracks, protrusions, and fissures on its surface, showing that there has indeed been activity on this moon. In fact, one of the objectives of the Cassini-Huygens mission was to find out whether this geological activity was still taking place today. Take a close look at these images taken by the Cassini probe. You can see 4 strange blue faults running parallel down towards the South Pole. These faults have been nicknamed the Tiger Stripes. 120 kilometers, or 75 miles long, they are several hundred meters deep and bear disturbing similarities to earthly faults. The probe's thermal sensors recorded some surprising data at Enceladus's South Pole. While these faults should be colder than the rest of the moon, they radiate heat. In fact, the faults are on average 95 degrees Celsius or 200 degrees Fahrenheit hotter than the rest of the moon. The mystery surrounding Enceladus thickened when the probe changed its perspective. As Enceladus passes in front of the Sun, immense geysers can be seen, erupting from the Tiger Stripes. These immense jets of matter rise up to hundreds of kilometers. So, does Enceladus harbor an energy source like Io or Europa that could explain these geysers? The answer is yes. Like the 2 Galilean moons, friction generated by gravitational forces causes the moon to heat up and melt ice. As it approaches Saturn, the moon Enceladus undergoes a torsion that creates internal heating, exactly what happens when a piece of metal is bent. The jets observed by the Cassini probe are in fact liquid water vaporized in space, freezing on contact with its icy temperature. These jets are propelled at an impressive speed of nearly 200 kilometers per hour or 125 miles per hour. So there could be liquid water beneath the surface of Enceladus. The Cassini-Huygens space mission team programmed the probe to pass through these jets in order to sample particles and better understand their origin. After several passes, the probe detected some of the elements that make up living organisms. The discovery confirmed that yes, there could be life on Enceladus. The moon contains 3 elements needed to be considered potentially habitable: liquid water, a powerful heat source, and organic material. What would life be like on Enceladus? Around the Tiger Stripes, we'd be in a region of eternal snow, since it's been snowing on Enceladus for at least 100 million years. The sky would be black, and we'd have the impression of floating due to the low gravity. We wouldn't be able to see anything with the sun at our backs, but facing the sun, we'd be able to see the immense geysers cut through the light and fall to the ground in a thick white mantle. For the moment, there is no evidence that Enceladus harbors life. Cassini's instruments have not detected any trace of life as such. But Enceladus is definitely on the list of next destinations to visit during space exploration missions. What's more, to analyze the moon's underground water content, you don't have to dig as you do on Europa. Just walk through the geysers. All the particles are sent into space, ready to be collected and analyzed. Apart from the Saturnian and Jovian systems, are there any other moons in our solar system that could potentially be habitable? Of the 214 moons identified by NASA, there must be more. To answer this question, scientists have turned to Uranus, Neptune, and Mars. Uranus and Neptune were overflown in the 1980s by the Voyager 2 probe. Scientists held out little hope of the habitability of these icy planets, which could not harbor liquid water, but after the discovery of oceans in unlikely places, the data collected on these planets and their satellites was revised. Uranus has 27 moons, but only 5 have been analyzed in depth: Titania, Oberon, Umbriel, Ariel, and Miranda. If an internal ocean existed on Miranda, the smallest of the satellites studied, it would probably have frozen over by now. But it's entirely possible that the other 4 moons contain an internal ocean. Depending on the moon, scientists have developed different scenarios to explain the origin of an energy source. On Titania and Oberon, the 2 largest satellites, heating is thought to be due to the tidal effect of Uranus, while on Ariel, it could be explained by cryovolcanic activity. The scientists' conclusion is that there may be internal oceans on the Uranian satellites, but they are relics of former oceans, or residual oceans, rather than thick oceans. And what about Neptune? The 8th planet from the Sun, Neptune, like Uranus, is what we call an icy planet. Of its 14 satellites, the one that most interests researchers is Triton, its largest, with a diameter of just over 2,700 kilometers, or 1,700 miles. Triton is an astonishing moon. It's the only known large satellite in the solar system to orbit in the retrograde direction, i.e., in the opposite direction to the planet's direction of rotation. For this reason, Triton may be a Kuiper Belt object captured by Neptune. It is also the only moon, along with Phobos, one of Mars' 2 moons, to approach the object around which it orbits. Our moon, on the other hand, is moving away from the Earth by about 3.8 centimeters, or 1.5 inches per year. While flying over Triton, Voyager 2 observed geysers 8 kilometers, or 5 miles high, over 180 kilometers, or 60 miles, all concentrated in the region of Triton, currently facing the Sun. These geysers would therefore have a solar origin. Researchers believe that Triton harbors fairly recent cryovolcanic activity, which explains the nature of the terrain observed by the Voyager 2 probe on its surface. Like Europa, Ganymede, Titan, and Enceladus, Triton could be home to an underground liquid ocean. To find out more, a mission project had been developed, the Trident mission, but it was not selected to be part of NASA's Discovery program. Instead, missions to Venus were chosen. No doubt another mission will be developed to answer the many questions scientists have about this mysterious moon. Where do its geysers come from? Why is its landscape constantly changing? Why does it have an intense ionosphere? Let's end our exploration of the mysterious moons of our solar system by getting a little closer to Earth. We're on our way to Mars and its two moons, Phobos and Deimos. These two moons share many characteristics with C-type asteroids, primitive bodies dating back to the genesis of the solar system. But contrary to what researchers have long believed, these are not primitive celestial bodies that were attracted to Mars from the asteroid belt like Triton. Not only is Mars' gravitational pull too weak, but their orbits are too circular. Phobos and Deimos are more likely to be the result of a collision between Mars and a giant celestial body. Perhaps these two moons were born at the same time, but their trajectories are different. Phobos is approaching Mars by around 2 meters every 100 years, while Deimos is moving away. In fact, Phobos is the closest satellite to its planet in the entire solar system. Its surface is dotted with craters, fissures, and other marks left by meteorite impacts. According to the researchers, Phobos will be destroyed in 30 to 50 million years due to deformations caused by Mars's tides and gravity, while Deimos will probably move away and emancipate itself from Mars' gravitational pull. In any case, these two moons are unlikely to harbor life. In the quest for extraterrestrial life, it's Mars that interests researchers. Europa, Ganymede, Callisto, Titan, Enceladus, Triton. All these moons could be inhabited by forms of life we can't yet imagine. Research carried out in recent years on the moons of our solar system has shown us that there are worlds not so far away from us that are very different from our own, and yet could be home to extraterrestrial life forms. Here's an image of the so-called Pillars of Creation in the Eagle Nebula, or NGC 6611. These columns of interstellar dust are in fact a star-forming zone at the heart of one of the most productive star-forming zones in the Milky Way. This photo dates back to 1995. It was taken by the Hubble Space Telescope, the predecessor of the James Webb, which was launched in 1990. Now take a look at this photo, taken in October 2022 by the NIRCam infrared camera of the James Webb Telescope. The difference is striking. It's like putting on glasses for the first time. A second image was taken by the James Webb's MIRI instrument, the only one that can see in the mid-infrared. This image is darker, and the stars can't be seen as clearly as in the first image, but it's still very impressive. It's the infrared vision of James Webb's instruments that allow us to see through the clouds of gas and dust and distinguish all these stars. The image is so detailed that it's easy to interpret. You can clearly see red dots representing baby stars, only a few 100,000 years old, and red streaks in the clouds of dust and gas that are actually nascent balls of gas that will later become stars. There's no shortage of examples of images that have been recaptured by the James Webb with greater sharpness and precision than those taken by Hubble. Why? Because the James Webb, unlike Hubble, observes the universe in the infrared. This enables it to capture the rays of the first stars, which were emitted in ultraviolet form, but whose wavelengths, stretched by the expansion of the universe, then shifted towards the red. the more pronounced the redshift, the more distant and ancient the star. Between May and September 2023 alone, the James Webb produced an impressive number of images of stunning sharpness and detail. Colliding or merging galaxies, stellar nurseries, gigantic black holes, magnificent nebulae. The Space Telescope lets us see what we can never see with the naked eye, not only because it's too far away, but also because our eyes can't see in these wavelengths. These images will undoubtedly help us to better understand the genesis of the universe, but also to advance our search for extraterrestrial life, somewhere in the universe beyond our solar system. For the first time, the James Webb is fully capable of analyzing the atmosphere of an exoplanet. A huge step forward, given that the composition of an exoplanet's atmosphere can give us important clues about its chances of harboring any form of life. For a planet to be potentially habitable, it needs to bring together a number of ingredients, none other than those required for the development and maintenance of life forms. On Earth, life has been able to develop thanks to liquid water, a source of energy in elements such as carbon dioxide, hydrogen, and oxygen. For an exoplanet to be habitable, it must therefore be located at a certain distance from its star, so that temperatures remain moderate and allow water to be maintained in liquid form. But it must also have the right chemical elements, a source of energy, such as volcanic activity, and an atmosphere to protect living organisms from the dangerous radiation emitted by its star. Of the more than 5,500 exoplanets discovered to date, researchers are nurturing the hope of one day finding one that meets the necessary conditions and on which a form of life could be discovered. You're about to find out how the James Webb Space Telescope can help us in this quest. To analyze the atmosphere of an exoplanet, we wait for it to pass in front of its star. This is called a transit. In this way, we can receive the light from the star that has passed through the planet's atmosphere. Thanks to this method, the James Webb's instruments will be able to identify the planet's chemical composition. The James Webb has two types of instrument: cameras to take images, and spectrometers to observe light spectra. While the general public is most fascinated by the images taken by the telescope, it's the spectrometers that are of most interest to scientists. Here's how a spectrometer works. Light passes through a lens, much like a film camera. This lens concentrates all the light in a single point, so that it can then pass through a narrow slit. The light then passes through a second lens and a prism, which breaks the light down into a number of colors like a rainbow. We can then distinguish the colors that make up the light. The light spectrum is a treasure trove of information. A light spectrum is distinguished by the black lines through which molecules reveal their identity by absorbing light. This is because molecules in space will absorb certain wavelengths of light. Each molecule has its own signature. Nitrogen, hydrogen, or sodium do not have the same spectrum. By analyzing these black lines, we can identify the signature of calcium, nitrogen, or hydrogen. It's as if the molecules left their fingerprints on the light spectrum. The James Webb spectrometers have been specially designed to detect the fingerprints of molecules in the infrared part of the light spectrum. The molecules of interest in our search for extraterrestrial life are those associated with life: carbon monoxide, carbon dioxide, hydrogen, and methane. Among James Webb's notable contributions is his study of WASP-39b, an exoplanet located 700 light-years from Earth in the Virgo constellation. WASP-39b is a gas giant slightly larger than Jupiter. However, it is much less dense than Jupiter, which facilitates observations. In fact, its atmosphere is puffier and more extensive, making it easier to detect the molecules that make it up. Hubble had already studied WASP-39b and detected water vapor in its atmosphere. James Webb's more detailed instruments have enabled us to find out more. In WASP-39b's atmosphere, scientists detected a molecule essential to life: carbon dioxide, or CO2. On Earth, CO2 is produced naturally through geological processes and is vital for plant growth. James Webb also detected sulfur dioxide in WASP-39b's atmosphere, the first time this molecule has been detected on a planet outside the solar system. Once again, this discovery marks a turning point, since sulfur dioxide, present in our ozone layer, plays a crucial role in absorbing part of the sun's UV radiation, which is harmful to the Earth and to us. However, WASP-39b lacks some important elements to make it a candidate for life as we know it. Firstly, a solid surface. For this planet is a gas giant, and not like Earth, a rocky planet. The results are still uncertain. It may have no atmosphere, but it may have a very thin one. The second missing element is a moderate temperature that would allow water to remain in liquid form. On WASP-39b, the temperature is over 870 degrees Celsius, or 1600 degrees Fahrenheit. The exoplanet is even closer to its star than Mercury is to the Sun. Although WASP-39b is clearly not habitable, the observations made by James Webb are still very useful and exciting for researchers. Above all, they provide a better understanding of the chemistry of exoplanet atmospheres. Astronomers hope to be able to establish models for the formation and evolution of exoplanets by better understanding their atmospheric evolution. In the case of WASP-39b, scientists believe it was formed by the collision of small rocky bodies, which merged to form an exoplanet. The exoplanet then moved closer to its star as it evolved. To provide such precise data, the telescope had to be calibrated over a long period of time. After its launch on December 25, 2021, the James Webb took a month to reach its L2 orbit point, located around the Lagrange point, 1.5 million kilometers, or 930,000 miles from Earth, on the opposite side of the Sun. Once in orbit, a further 5 months of calibration were required, meaning that the first images taken by the telescope were not released until July 2022. It was particularly important to ensure that the James Webb was working properly before launch. Adjustments had been made to Hubble to correct faults that were only detected after it had been put into orbit via a mission by the U.S. Space Shuttle Endeavour in 1993. But in the case of James Webb, post-launch corrections were unthinkable, given that the telescope orbits 1.5 million kilometers from Earth. Fortunately, no anomalies were reported when the telescope went into operation in early 2022. The launch performed by Ariane 5 was perfectly executed, which means that the telescope still has fuel reserves for 26 years, far more than the 5 to 10 years originally hoped for. Teams monitoring the telescope are taking great care to ensure that no micrometeorites hit its mirror, or any other accident that would bring the James Webb mission to an early end. Calibration of the James Webb took several months. This step is very important to ensure the reliability of the telescope's discoveries, in particular, the age of early galaxies. If the data are not reliable, this will have an impact on the veracity of our knowledge of our universe. To calibrate the space telescope, a team used the globular cluster Messier 92 as a reference. As one of the brightest and oldest groups of stars, it has been widely observed, and a wealth of reliable data is available. This team of researchers therefore compared the data returned by the James Webb with what was already available, and adjusted the instruments and sensors accordingly. No easy task, since the James Webb has no fewer than 18 sensors. Once the calibration had been fine-tuned, the scientists were able to start measuring the brightness of distant galaxies to deduce their distance with great precision. For the moment, the most distant galaxy, the first galaxy, has yet to be identified, but researchers are not giving up hope. Thanks to this calibration, the images we can see today are not only magnificent but also realistic. Or at any rate, researchers are working to make them as faithful as possible to what the telescope observed, while adapting the images to our human eye. The images you can see, such as the phantom spiral galaxy, NGC 628, the Carina Nebula, Jupiter and Neptune with its rings, have all been reworked. The very first image taken by the James Webb left a lasting impression. It was unveiled on July 11, 2022. In this image of the deep universe, we can see the galaxy cluster SMACS 0723, made up of thousands of galaxies, and celestial objects of very low brightness. But this image was not broadcast as it was taken. It was produced by compiling images taken by the James Webb at different wavelengths over a period of 12.5 hours. The result is the sharpest infrared view of the distant universe ever obtained with a telescope. How are images taken by the James Webb reworked? The human eye can only see a very narrow part of the light spectrum, from violet to red, i.e. the colors of the rainbow. But the light spectrum is much broader than that, with light on both sides of the spectrum. The James Webb focuses on the infrared, so it can see farther than the human eye on the red side of the light spectrum. These are the data imaging developers who rework the images taken by the James Webb's near and mid-infrared instruments. In addition to computer skills, this job requires an artistic flair. It involves transposing infrared light into colors that our eyes can distinguish, i.e., one of the colors of the famous rainbow. The James Webb takes several successive images of the same celestial object with different infrared filters at different distances. The different wavelengths, i.e. near, mid, and far infrared, are then converted into the colors of the rainbow, according to the rules of data colorization, known as chromatic order. The principle is simple. Data is captured in the infrared, then shifted to the visible part of the spectrum. The principle is the same as transposing a song played on the piano into a different key. The melody remains the same. Thus, the farthest wavelength will be red, the middle wavelength green, and the closest blue. The filters are superimposed to create a colorized image. This image remains fairly flat, so it needs to be reworked one last time. It's this last stage that most calls on the developer's subjectivity and artistic sense. The idea is to obtain an image that is beautiful to look at without removing or adding elements, while remaining as faithful as possible to reality. We're now going to take a look at the latest images taken by the James Webb Telescope, which have enabled researchers to advance a little further in their quest for knowledge about our universe. Let's begin our exploration with a discovery that is one step closer to finding a habitable world beyond our solar system. On September 12, 2023, NASA reported that the James Webb had found gas showing the presence of an ocean on a planet 120 light-years from Earth, the planet K2-18b. The telescope found traces of molecules such as carbon, methane, and carbon dioxide, which could indicate that this exoplanet is covered by an ocean with a hydrogen-rich atmosphere. K2-18b would therefore be a high-oceanic planet, i.e. an ocean planet with a predominantly hydrogen atmosphere. In fact, Hubble had already found traces of water vapor in this planet's atmosphere, but the James Webb observations once again confirm scientists' suspicions. The James Webb also discovered a molecule called dimethyl sulfide, or DMS. This molecule is only produced on Earth by life, notably phytoplankton. On K2-18b, there may therefore be the equivalent of terrestrial phytoplankton. This discovery is therefore very promising and could be a clue to life on a planet in the near universe. All the more so as K2-18b is located in its star's habitable zone. NASA remains cautious and has made it clear that further checks are required to confirm the presence of an ocean on this planet. In any case, the information gathered by the James Webb is best interpreted by this hypothesis of an ocean on the planet's surface. The most widely accepted hypothesis at present is that, like Neptune, K2-18b harbors a vast high-pressure ice mantle with a surface ocean and a thinner, hydrogen-rich atmosphere. The ocean, however, would be too hot to be liquid or habitable. Confirming this hypothesis will be complicated, even with the prowess of the James Webb. Indeed, the brightness of this exoplanet's parent star is so low that when the planet transits in front of it, only a tiny fraction of the light reaches the telescope. However, just 2 observations have yielded a wealth of interesting data, and further observations are in progress. So it's a safe bet that we'll soon have new information about this planet. On the other hand, some scientists remain skeptical about the concept of a high oceanic planet. Admittedly, models and simulations show us that they could very well exist. But the existence of water in liquid form is subject to very precise parameters with very small windows, and all it takes is for one of them to move just a little for water to no longer exist in liquid form. For example, a certain level of hydrogen in the atmosphere of an exoplanet can guarantee water in liquid form on its surface, but if there's just a little too much hydrogen in the atmosphere, the water no longer exists in liquid form, but in supercritical form. Or, as on Earth, mechanisms would have to exist to stabilize the conditions that make it possible for water to exist in its liquid state. However, it is unlikely that all oceanic planets possess the same plate tectonics and volcanism mechanisms as Earth. All we can do now is wait for further data from James Webb to find out more about this exoplanet and about oceanic planets in general. Let's move on to another James Webb discovery. Take a look at this image. It was taken by the James Webb on August 31st, 2023. You can see Supernova 1987A, or SN 1987A, one of the best-known supernovae. Located 168,000 light-years away in the Large Magellanic Cloud, it has been observed for almost 40 years. Why, if it's already known, has this supernova been observed again with the James Webb? What did astronomers expect to discover? Quite simply, because astronomers hope to use it to understand how a supernova develops over time. To better understand James Webb's recent discoveries, let's take a look back at the story of this supernova's discovery. As its name suggests, SN 1987A was discovered in 1987, in the month of February. The discovery was made by Chilean astronomers Ian Shelton and Oscar Duhalde. It is a Type II supernova, i.e. the result of the gravitational collapse of a massive stellar core that has exhausted its nuclear fuel. Let's keep it simple. Originally, there was a star called Sandalik 69202, a blue supergiant born 10 million years ago from a stellar collision with fusion. This star had a mass 20 times that of our Sun. When the star ran out of fuel, it was unable to maintain a balance between the gravitational forces and the pressure forces generated by nuclear fusion. Eventually it exploded, releasing a large amount of light and matter into space, resulting in a Type II supernova. SN 1987A was the first supernova to be observed with the naked eye since the dawn of modern astronomy. Since its discovery, telescopes around the world have observed this supernova, including NASA's Chandra X-ray Observatory, which has examined it repeatedly, during 17 years of scientific operations. Between 1999 and 2013, Chandra's data showed an expanding ring of X-ray emission that grew brighter and brighter, certainly produced by the shock wave from the supernova's explosion. Hubble had also observed this supernova, so it made sense to continue observations with James Webb. The photograph taken by the James Webb Telescope has enabled scientists to advance their understanding of this supernova. At the center of the supernova, you can see a keyhole formed by the matter ejected from the supernova, namely gas and dust, a structure that has never been observed before. To the left and right of this keyhole structure, you can also see crescents, shapes recently discovered by the James Webb. Beyond the center of the supernova, you can see an equatorial ring of material ejected tens of thousands of years before the supernova exploded. This equatorial ring contains bright hot spots that formed when the shock wave from the explosion caught up and heated the material in the ring. Around the equatorial ring, you can make out two faint outer rings, which according to researchers are the result of the interaction between the star's stellar wind emitted before the supernova and the matter previously ejected by the star. Unfortunately, the dust at the center of the supernova is so dense that not even the near-infrared light detected by the James Webb can penetrate it. That's why the keyhole is so dark in the photo. The telescope, although very advanced, was therefore unable to detect the supernova's residual star. Yet this is what scientists had hoped to observe. In fact, the collapse of a star's core, as happened with SN 1987A, usually leads to the formation of a neutron star or a black hole. In the case of this particular supernova, it would be a neutron star. Astronomers hope to be able to observe this neutron star once the gas and dust in the supernova's inner region have dissipated slightly. James Webb's next discovery we're going to talk about concerns Herbig-Haro objects, abbreviated as HH. Herbig-Haro objects are luminous regions surrounding newborn stars. When stellar winds or jets of gas spewed out by newly born stars create shock waves, and these shock waves collide at high speed with nearby gas and dust, Herbig-Haro objects are formed. On September 14, 2023, an image of the object Herbig-Haro 211, or HH211, was released. Located in the Perseus constellation, around 1,000 light-years from Earth, HH211 is a protostar that looks very much like our Sun when it was only a few tens of thousands of years old. Its mass is currently only 8% that of our Sun. HH211 had already been observed from the ground, but this is the first time we've been able to see it in such detail. The James Webb Telescope also photographed HH797, an object located in the immediate vicinity of star cluster IC 348, at the edge of the Perseus molecular cloud, around 600 light-years from Earth. Observing this object from the ground, astronomers had noted that the cold molecular gas associated with HH797 had a double motion. To the south, there was a redshift, meaning that the region was moving away from us. To the north, there was a blue shift, indicating that the region was moving towards us. Thanks to James Webb's observations, astronomers were able to distinguish two parallel jets instead of one, each with its own speed and history. This could mean that HH 797 is around a double star, and not, as astronomers have long assumed, a single star. Herbig-Haro objects are fascinating phenomena. The speed of the stellar winds and gas jets released by newly born stars is dizzying, and the shock waves created by the collision between these energies and the surrounding gas and dust are impressively powerful. These objects show us that within a star-forming zone, there are intense dynamics and energy flows that are both complex and incredible. With its infrared instruments like the NIRCam, the James Webb is perfectly equipped to observe newborn stars and Herbig-Haro objects, and thus better understand the dynamics at work during star formation. Let's continue our exploration of recent discoveries by the James Webb Telescope. On October 10, 2023, the James Webb observed the brightest star-forming region of the Small Magellanic Cloud, NGC 346. The Small Magellanic Cloud, also known as SMC or NGC 292, is a satellite galaxy of the Milky Way, and thus part of the local group, our group of galaxies. This irregular dwarf galaxy is visible to the naked eye in the southern constellation Toucan. It's one of the most distant objects visible to the naked eye, located some 199,000 light-years from Earth. In fact, you can only see it from the southern hemisphere, in a place far from pollution. The Small Magellanic Cloud should not be confused with the Large Magellanic Cloud, with which it forms a pair. The two are linked by the so-called Magellanic Bridge, a bridge of gas and stars. It's the Small Magellanic Cloud that interests us here, as it was in this galaxy that the James Webb was able to observe NGC 346, a particularly bright star-forming region. This image of NGC 346 was taken by James Webb's MIRI instrument. NGC 346 is a region in which stars are regularly born. It has already been photographed by Hubble, so this is not the first time it has been observed by astronomers. However, the near-infrared images taken by James Webb in January, followed by mid-infrared images in October, have enabled us to refine our knowledge of this region. The James Webb images show bands of gas and dust, dotted with luminous spots, filled with young protostars. Astronomers were astonished that the images revealed cold gas and dust emissions. The Small Magellanic Cloud is a more primitive galaxy than our own, so astronomers expected it to be fairly dust-poor. In fact, this neighboring galaxy contains fewer heavy elements than the Milky Way. Heavy elements are forged in stars by nuclear fusion and supernova explosions, so they appear late in a galaxy's lifespan. The Small Magellanic Cloud must contain heavy elements, since it is heavy elements such as silicon and oxygen that are responsible for the formation of galactic dust. The James Webb images show polycyclic aromatic hydrocarbons and dusty silicates, as well as dust heated by the most massive and brightest stars, shown in red in the photos. Bright spots and filaments can also be seen, concealing a large number of protostars. The researchers counted 1,001 red stars, most of them young stars masked by dust. The images of NGC 346 are important because they will give us a better understanding of the more primitive galaxies that existed billions of years ago, at a time called cosmic noon, when star formation was at its peak and heavy elements were present, but in lower concentrations than today. Here is an image of another star-forming region taken by the James Webb's NIRCam, which immediately struck the general public with its sharpness and detail. This is Sagittarius C, or SGR-C, a star nursery at the center of the Milky Way. This image has made an indelible impression on the general public, as well as on researchers, because until now, infrared data on this region had never been obtained with such a high level of sensitivity. Offering unprecedented detail, the image revealed many previously unobserved features of this region. According to the researchers, the center of the Milky Way is the most extreme environment in our galaxy. Sagittarius C is located very close to the center, just 300 light-years from our galaxy's supermassive black hole, Sagittarius A. This star-forming region is therefore quite far from us, at 25,000 light-years from Earth. In this image, we can see around 500,000 stars and clusters of protostars, i.e., stars in the process of forming, or if you like, baby stars, and all in a volume about 50 light-years across. One of these protostars is particularly massive, with an estimated mass 30 times that of the Sun. This protostar blocks the light behind it, so James Webb was unable to see all the stars in Sagittarius C. This is a pity, as the area hidden by the massive protostar promises to be one of the densest. The darker areas visible in the image are also star nurseries. More precisely, they are Bok globules, i.e., dark clouds of dust and gas, in which the birth of stars can begin. But what most intrigues researchers is this region, shown in cyan blue, which extends over 25 light-years and is made up of ionized hydrogen. Typically, hydrogen is ionized by energetic photons emitted by massive young stars, but in this case, it's the sheer size of the area that has astronomers wondering. On top of this, researchers are puzzled by the needle-like structures seen in the photo, which appear to be oriented chaotically in several directions. These structures are astonishing, and for the moment, astronomers have no explanation. This is the first time such structures have been observed in the heart of the Milky Way. In any case, this highly detailed image confirms that the center of our galaxy is a tumultuous zone, boiling with energy. Clouds of magnetized gas form stars, which in turn emit stellar winds, jets, and radiation that impact on the surrounding gas and create impressive objects. An extreme environment that researchers are only just beginning to study. James Webb's detailed images will undoubtedly be a great help in the quest to understand star formation at the heart of our galaxy. Among James Webb's most significant discoveries at the end of 2023 was the discovery of a never-before-seen jet stream near the equator of Jupiter. This impressive discovery was made by comparing James Webb images with those from Hubble. It was subsequently published in the renowned journal Nature on October 19, 2023. It brought to light a feature of Jupiter that had never been seen before. According to NASA, it's a high-speed jet stream, moving at around 515 kilometers per hour, or 320 miles per hour, twice as fast as a Category 5 hurricane. In fact, it's a well-known phenomenon, even though it has never been observed on Jupiter before. A jet stream is a tube of strong winds located around 8 to 15 kilometers, or 9 miles in altitude, at the boundary between the troposphere and the stratosphere. The one detected by James Webb lies above Jupiter's equator, at around 40 kilometers or 25 miles above the clouds, and extends over 4,800 kilometers or 3,000 miles across. This discovery gives us our first glimpse of how the layers of Jupiter's atmosphere interact with each other. According to the researchers behind the study, published in the journal Nature, Jupiter has a complex pattern of winds and temperatures, and the jet stream that has been spotted could vary considerably over the next 2 to 4 years. It will be further studies by the James Webb that can help us determine whether the jet's speed and altitude tend to evolve over time. On July 27, 2022, the James Webb Telescope had already delivered unprecedented images of Jupiter. These were perfectly sharp, well-defined images, revealing details of the largest planet in our solar system. The James Webb images, taken with the NIRCam near-infrared camera, reveal Jupiter's rings, its smaller satellites, Amalthea and Adrastea, and above all its polar auroras, 100 times brighter than those seen on Earth. Jupiter's polar aurorae are caused by the encounter of matter thrown up from the moon Io with the gas giant's atmosphere. A study carried out in August 2021, using recordings from the Keck telescope in Hawaii, had shown that these aurorae acted like a radiator, providing heat to the whole planet. The James Webb images of Jupiter also show the famous red spot, which appears white because it reflects sunlight. Jupiter's Great Red Spot is a gigantic anticyclone in the planet's atmosphere, located at 22 degrees south latitude. Although it's not necessarily obvious from the James Webb images, this red spot is slightly larger than our planet itself. In 2015, its dimensions were estimated at around 15,000 kilometers, or 9,300 miles in length, and around 12,000 kilometers, or 7,500 miles in width. In the past, it would have been even larger, since it is estimated that over the course of the 20th century, it has shrunk by half. In this anticyclone, winds are said to blow at 700 kilometers per hour, or 430 miles per hour. The Great Red Spot was so named around 1878, but today it appears rather brown. James Webb did not discover this red spot, as it has been known for over 350 years, and very clear images of the phenomenon had already been obtained, notably by the Cassini-Huygens mission. However, these images will enable scientists to better study the interaction between the dynamics of Jupiter's atmosphere, chemical composition, and temperature in and above the Great Red Spot. Here are a number of images taken by James Webb and now well known to all astronomy enthusiasts. In this image, taken on July 12, 2022, you can see a young star-forming region in the Carina Nebula, 8,500 light-years from Earth. A region that had already been photographed by Hubble, but never with such precision. In this image, taken on September 12, 2022, you can see the Orion Nebula, the closest nebula to us at around 1,350 light-years from Earth. Once again, this region had already been photographed by Hubble, but James Webb's photo revealed new details. The image in front of you is very sharp. You can even make out Orion's bar, a wall of gas and dust inside the nebula, and two very bright stars that are part of the trapezium cluster. We can also see a cocoon of stars with a protoplanetary disk, conditions similar to those that led to the birth of our Sun and its planets 4.5 billion years ago. Another nebula was also photographed by James Webb on September 6, 2022, the Tarantula Nebula. Located 161,000 light-years from Earth in the dwarf-large Magellanic Cloud Galaxy, this nebula is the largest and brightest star-forming region in the entire group of galaxies not far from the Milky Way. This nebula is also home to the hottest and most massive stars known. For all these reasons, the Tarantula Nebula is of great interest to scientists. Here's a final image taken in 2022, on July 12th to be precise, by the James Webb. It shows the Southern Ring Planetary Nebula, located around 2,500 light-years from Earth, in the constellation of the Veils. James Webb's image enabled scientists to discover the origin of this planetary nebula, a binary system of dying stars. On October 30th, 2023, the James Webb unveiled a new nebula image, the Crab Nebula. Located 6,500 light-years away in the constellation Taurus, this nebula is in fact a supernova remnant. The Crab Nebula had already been photographed by Hubble in 2005, but here again, the details provided by the James Webb images have enabled scientists to better understand its origin. The James Webb data have enabled us to establish the composition of the ejected material, in particular its iron and nickel content, which will tell us what type of explosion produced the Crab Nebula. By the way, take a look at the two images side by side, the Hubble image and the James Webb image. You can see that in the James Webb image, there's more detail in the central regions of the nebula, where you can see the emission of dust grains. The orange filaments you can see in the image taken by the James Webb are the remains of a star that has now disappeared. The supernova created by the explosion of this star was seen on the Asian continent in 1054. For 23 days, the supernova shone brightly and could even be seen in broad daylight. Even today, the nebula continues to expand at a speed of 1,500 kilometers per second, or 930 miles per hour, as a result of this explosion. In the center of the image, you can see a translucent zone of what is known as synchrotron radiation. Synchrotron radiation is generated by the presence of a pulsar, a neutron star that rotates very rapidly and emits strong radiation. Thanks to these breathtaking details, scientists hope to glean valuable information for a better understanding of a star's life cycle. The image before your eyes is considered one of the most complete views of the universe ever obtained. This image has been reconstructed using James Webb and Hubble images. It shows the MAX 0416 galaxy cluster, 4.3 billion light-years away. More precisely, MAX 0416 is a pair of colliding galaxy clusters which will eventually merge to form an even larger cluster. Researchers combined images taken in visible light by the Hubble telescope and in infrared by the James Webb telescope to reconstruct this colorful view of our universe. In fact, why is this image so colorful? Quite simply, because it shows thousands of galaxies that appear differently colored according to the wavelength range in which they shine, i.e., from 0.4 to 5 microns. The nearest galaxies, regions of intense star formation, appear in blue and were detected by Hubble. The most distant galaxies, on the other hand, appear in red and were detected by James Webb, as they are too far away for Hubble to see. Objects colored green are located at mid-distance. James Webb didn't just take a picture of this cluster of galaxies at a given moment in time. He observed the region 4 times, a week apart, to identify what are known as transient objects. Transients are objects whose brightness varies over time. 14 transient objects were detected, 12 of which are likely to be single stars or multiple star systems, and 2 are likely to be supernovae. This means that transient phenomena could be much more numerous than previously thought. Among the transient phenomena identified in the MAX 0416 cluster, one in particular has caught the attention of scientists. This is a giant star that has been nicknamed Mothra because of its monstrous nature. It is located in a galaxy that existed some 3 billion years after the Big Bang and is amplified by a factor of at least 4,000 through gravitational lensing. Mothra was already visible in Hubble's observations almost 10 years ago, which is quite unusual. Indeed, it would take a very specific alignment between the galaxy cluster in the foreground and this star in the background for it to be so amplified. However, the mutual movements of the star and the cluster should have broken this alignment. The explanation put forward by the scientists is the presence of an additional object in the foreground group, which would add magnification, like a globular cluster. This object would have a mass between 10,000 and 1 million times that of our Sun. The MAX 0416 cluster has been nicknamed the Christmas tree cluster because, according to NASA researchers, it is very colorful with flickering lights, like the lights on the tinsel of a Christmas tree. Among the most recent images taken by the James Webb is this impressive photograph. This is no trick. This cosmic ghostly figure is a galaxy in formation called Aztec 71, more precisely, a dusty star-forming galaxy. This is a type of galaxy hitherto reputed to be very rare and almost invisible. Hubble had already attempted to photograph this galaxy in formation, but without any real success. Aztec 71 is very difficult to observe. This galaxy is the seat of star formation, but it's shrouded in a dusty veil that's very difficult to penetrate. That's why Hubble, which couldn't see in the infrared like James Webb, wasn't able to obtain satisfactory images. James Webb's image, broadcast on October 10, 2023, is very striking. It looks like a ghostly face. It looks like a tiny drop in the vastness of the universe. But this galaxy is actually forming hundreds of new stars every year. This discovery shows us that there could be a whole population of galaxies hiding from us that we won't be able to observe until we develop even more powerful instruments than the James Webb, capable of seeing in even more extreme wavelengths. This discovery has also led researchers to claim that this type of galaxy, thought to be extremely rare, is in fact 3 to 10 times more common than previously thought. Like the image you've just seen, this photo of the exoplanet WASP-107b, taken by the James Webb, is also very impressive. WASP-107b is a gas giant, orbiting a highly active K-type main sequence star, located around 200 light-years from Earth. It is nicknamed the Hot Super Neptune. One of its special features is that it is one of the exoplanets with the lowest known density. Its mass is only 12% that of Jupiter, while its diameter is comparable. This is due to the fact that its atmosphere is greatly expanded by the radioactive heating of its star, around which it orbits in just 6 days. Temperatures in its atmosphere reach hundreds of degrees. WASP-107b's highly expanded atmosphere has earned it the nickname of Cotton Candy Planet. In any case, it facilitates measurements of the planet's atmospheric spectrum. Astronomers had already discovered helium in its atmosphere thanks to Hubble's observations. Observations by the James Webb have taught us new things about this cotton candy exoplanet. The data provided by the telescope was analyzed by a team of European astronomers, co-led by researchers from CEA and the Institute of Astronomy at the Belgian University KU Leuven. The scientists were able to detect silicate clouds in WASP-107b's atmosphere, a first for a planet of this type. According to their analysis, WASP-107b's atmosphere contains not only clouds of silicate particles, cousins of sand grains, but also molecules of water vapor and sulfur dioxide, SO2. Surprisingly, however, no traces of methane were found. This remains unexplained for the moment, unlike other discoveries such as sulfur dioxide, which have been elucidated by new models, astrophysicists still don't understand why no trace of methane has been detected in the atmosphere of WASP-107b, which might force them to revise the models of exoplanet atmospheres known to date. Nevertheless, if the discovery of silicate clouds initially surprised scientists, it can be explained. What astonished astronomers was the presence of these clouds at high altitude. The temperature is only 500 degrees Celsius or 930 degrees Fahrenheit at this altitude, yet the melting temperature of silicate particles tells us that they should form deeper in the atmosphere at higher temperatures. Surprisingly, sand clouds exist and persist at high altitudes. In fact, it would seem that the phenomenon is roughly similar to that of the water cycle on Earth, except that rain is not made up of drops of water but of sand. The droplets of sand rain evaporate into deeper, hotter layers, and the resulting silicate vapor is then carried upwards, where it recondenses to form silicate clouds once again. A discovery that overturns our understanding of exoplanet atmospheres. WASP-107b appears to be an exotic world, completely different from our own, with complex chemical interactions. There is no equivalent of this exotic world in our solar system, and that's what's so fascinating. Here's another image that may not mean much to you, but represents a real breakthrough for astrophysicists. This image is none other than the discovery by the James Webb Telescope of the most distant black hole ever detected in X-rays. This discovery was made possible by the combination of two space telescopes, the James Webb and Chandra. Because it emits X-rays, we know that it is a supermassive black hole in full growth. The study of this black hole will be invaluable in understanding how some of the first supermassive black holes in our universe were formed. Most astrophysicists agree that there are compact stars at the heart of the vast majority of large galaxies, containing at least 1 million and sometimes several billion solar masses, and behaving as predicted by black hole theory. In other words, supermassive black holes. What we don't know is how these supermassive black holes came to be. There are a number of theories. One of the most widely accepted is that black holes are formed by the accretion of matter from cold filaments. What are cold filaments? They are filaments of cold gas, channeled by filaments of dark matter, which are thought to feed the star-forming matter that makes galaxies grow. Many other hypotheses have been considered. The existence of primordial stars of very high mass, the existence of giant black holes produced during the Big Bang. The discoveries of the James Webb Telescope should enable us to find out more. Let's return to our image. First, Chandra, a space telescope in orbit since 1999, detected a source of X-rays in the UHZ1 galaxy, in the direction of the Able 2744 or Pandora cluster of galaxies, 3.5 billion light-years from the Milky Way. The Pandora cluster, thought to have resulted from the merger of 4 smaller galaxy clusters, is particularly rich in dark matter. This creates a useful gravitational lensing effect for astronomers, making it easier to observe distant galaxies in the visible or near-infrared range. From the data collected by James Webb, researchers were able to establish that galaxy UHZ-1 is seen as it was only 470 million years after the Big Bang. As for the Chandra data, they show that the X-ray source associated with this galaxy has all the characteristics of a growing supermassive black hole. This would make it the most distant black hole ever observed in X-rays. What's more, this black hole would have unusual characteristics. With a mass 10 to 100 million times that of the Sun, it contains a quantity of matter equivalent to that of all the stars in the galaxy where it lived in a past revealed to us by photons that traveled more than 13 billion years. We are therefore observing a black hole at an extremely early stage, with a mass similar to that of its host galaxy. According to the researchers, this is a very brief phase in the life of a black hole, during which it weighs about as much as the stars in its galaxy, before falling behind. All these observations confirm the hypothesis that supermassive black holes are the result of a gravitational collapse of a very large gas cloud. Since its launch at the end of 2021, the James Webb Telescope has enabled numerous advances in the fields of cosmology and astrophysics. Not only have new cosmic objects been discovered, but even more knowledge has been gained about the objects already photographed by Hubble, with captivating, colorful images packed with detail. The discoveries made by the James Webb have provided new insights that will not only help us better understand certain cosmic phenomena, but also advance our understanding of the phenomena at the origin of our universe. Here's a first example. In a study published on November 8, 2023, in the journal Astrophysical Journal Letters, a team of researchers explained the role of protoplanetary disks in planet formation, deduced from observations of the James Webb. Protoplanetary disks are agglomerations of gas and dust. They are home to icy rocks, which release water vapors under the effect of extreme temperatures. Protoplanetary disks are therefore predominantly composed of cold water. As they approach newborn stars, icy rocks evaporate, forming rocky planets. This phenomenon was certainly behind the creation of our solar system some 4.6 billion years ago. This hypothesis suggests that even in the most extreme environments of our galaxy, where protoplanetary disks are found, telluric planets like our own could form, which considerably widens the field of possibilities. Here's a second example of a discovery made thanks to the James Webb that has profoundly changed the theories of modern astrophysics. In the vicinity of the Big Dipper constellation, the James Webb Telescope has captured some very old galaxies that, according to our current theories, shouldn't even exist. The 6 galaxies discovered by the James Webb are estimated to have formed only 500 to 7 million years after the Big Bang. They are therefore almost 13 billion years old. However, according to the researchers' calculations, they could contain as many stars as the Milky Way, which doesn't fit our current models. According to currently accepted theories, there must not have been enough matter at that time for galaxies to form as many stars as the Milky Way. These discoveries call into question the very principle of the formation of the first galaxies. At first, because James Webb had already observed very old galaxies, formed around 350 million years after the Big Bang, but they were small and didn't contain as many stars. Galaxies that are both very old and massive, never before seen. It's possible that the red dots observed by the researchers are not very old galaxies, but quasars or supermassive black holes. Or they could be smaller galaxies than scientists have calculated. New data will be needed to confirm the discoveries and find out whether or not we need to revise our current theories and models. New data, that's what we're waiting for to complete all the somewhat disturbing discoveries made over the last 2 years by the telescope. Scientists are keen to make the most of James Webb's potential and use its mission to confirm and refute each of these strange discoveries. Above all, these observations are expected to enable us to reconstruct the history of the universe without any blanks. In fact, the ultimate goal is to fill in all the gaps in our understanding of the universe. How did the universe ignite? How did galaxies come into being? At present, we still don't know how to go back to the first instance of the universe. It's as if we had photos of the universe as a baby, arriving home from the maternity ward, but not of its very first moments. The very first memory we have of the birth of the universe is when it is 378,000 years old. The universe is then what we call the cosmic microwave background. It's made up of tiny specks, representing variations in density. The densest regions become galaxies and stars until they reach us. But how did these tiny specks create galaxies and stars? This period, which lasted several hundred million years when stars didn't yet exist, is known as the Dark Age of the universe. The universe was made up mainly of hydrogen, like a fog in the end, since hydrogen atoms reflect light radiation and we can't see through them. Our knowledge of the history of the universe lacks that moment when the universe emerges from the Dark Ages and the first stars and galaxies begin to take shape. This is what we'd like to understand with James Webb and future generations of telescopes.